Live.
Yes, we are live. Okay, so again, thank you to everyone who just competed in chemistry and biology and who listened to all of our lectures throughout today. We're now going to kick off the mathematics speaker panel, where we'll journey into actuarial mathematics, the relationship between algebra and geometry, the intersection between probabilistic combinatorics and mathematical theater, the connection between origami and math, and some questions about place value. To start off, we have the amazing Dr. Corina Constantinescu, a mathematics professor and the director of the Institute for Financial and Actuarial Mathematics at the University of Liverpool, who's going to take us on a journey through actuarial mathematics. Dr. Constantinescu worked as an actuary and led the life insurance department of one of the first private Romanian insurance companies. Dr. Constantinescu is actually joining us very close to midnight her time. So thank you so much for coming at such a late time to help us inspire the next generation of mathematicians. Without further ado, Dr. Constantinescu, please take it away.
Thank you. Well, thank you very much for the invitation, and I have to congratulate the organizers for this exceptional event that seems to go extremely well so far. And indeed, the energy is quite amazing to see. So as Diana said, I'm going to take you through a small journey in actuarial science and how I see actuarial science, and to answer a few questions like, why did I become a mathematician? For me, it was a way to make friends, and it's still a way to make friends because I love to work with others, and mathematical problems are the right kind of challenge and that generate discussions and very, very nice debates. And mathematics has a language of its own that it's very easy to speak, no matter where you are from. And that's always very inspiring. And I believe for everyone who loves mathematics that you know that finding the right solution, there is no kind of better reward than solving a problem and finding a solution. Now, why actuarial mathematics? Why an actuary? An actuary, if you work in industry, it's a business professional who would analyze the financial consequences of risk. So to do that, you would use mathematics and statistics and some financial theory to study uncertain future events. It's mostly used in insurance and pension programs, but it becomes more common to be used in other fields. And I am convinced that more and more risk managers will be needed in various areas outside insurance. Now, there are some societies that will have professional exams from which you would become a professional actuary. And one of them is the Institute and Faculty of Actuaries in the UK, and the other one is the Society of Actuaries in the US. Here in the picture is the magazine of the Institute and Faculty of Actuaries, this edition, August 2020. I'm proudly holding it because one of our research has been featured in it. And this is the first one I want to talk to you about. So insurance, for those of you that don't know, have a few branches. I will only mention 3 of them today. One of them being life insurance. So life insurance refers to pricing in the event of death, and it's related to pensions, and it's related to all sorts of annuities if you survive or if you die in an uncertain event. Now, usually families are insured, but never is considered that 2 spouses are in any way dependent on each other. Although there is a documented syndrome, the so-called broken heart syndrome, that occurs um, as a heart condition in a stressful or extreme situation, for instance, in the loss of a spouse. Now, in developed countries, Western countries, it's been documented as existing, and it manifests within the first year of what's called bereavement. So the first year after your spouse passed away, you are more likely, you are so affected by this that you are very likely to pass away as well. But as a positive of it, after a year, if you survive that year with the help of your family and friends, you would be recovering and having the same life expectation as anyone in your age group. We were wondering if the same will happen for African countries, where the community structures are different, where you tend to live with your family and with your close and not so close family. And the social structures, the fabric of the social structure is very, very different. And in this project that I work with one of my colleagues, Olivier, that's originally from Cameroon, and one of our students, Kira, that's from Liverpool, we have looked at Ghana in particular to see if indeed such a broken heart syndrome is prevalent there. And our observation was that, yes, it is, but it's not the same first year effect. It has a delayed effect, which probably is explained by longer funerals. The whole process of grieving has a very different format. And however, which again signals that in African countries, the looking after someone that just lost a spouse should be taken place not only on the first year, but in the second year after. Now, another research that interests me, and I work with some of my previous PhD students that now are academics on their own, is related to car insurance. The car insurance in a particular situation. I don't know how many of you know, but women in Saudi Arabia were not allowed to drive until the 24th of June, 2018. So 2 years ago, the ban on women driving a car has been lifted. So all of a sudden, the whole country of Saudi Arabia will have as drivers, not only men, but women. So this simple policy change has a huge effect in many aspects. One of them being insurance. How will you price a woman driver, a woman that has never driven before, that starts driving lessons in her 40s, for instance, and has no experience of driving in her life? And just to signal what kind of changes you see from such a policy change, one of the first ones is, as you see in this picture taken from CNN, women are happy that they do not need a driver. They don't need to call a driver. So all of a sudden, the jobs of these men that were just meant to drive women around has to be replaced by jobs of driving schools, someone to teach women to drive. And the fact that all of a sudden in traffic will be women drivers, the men driving around will also be affected by encountering on the other car a woman driver. And all of this will have an impact on how the behavior of drivers in traffic will evolve. Now, as you see here, the short-term impact, apart from driving lessons and driving schools, and of course more car will be sold and or leased, is the car insurance. And the biggest question is, how will you price? How much will you charge a woman that wants to drive? And how do you make sure that they are correctly priced? And for that reason, we are trying to propose a system that it's already available in many other countries. It's referred to as the bonus-malus system or a reward penalty system, where you look at the history of a driver and depending on how they drove in the past, you reward them or you penalize them. Of course, these women will have no history to begin with, so they will start at the basis premium or a basis tariff. But then as time passes, the company will have to make sure to reward them or penalize them based on their behavior. And we suggest the same for men so that the whole market will benefit from this system. Now, the last kind of insurance that I want to refer to is related to property insurance. This will be for houses. And now I'm going to talk about houses in Japan. You might know that Japan is what is called, it's placed on the so-called Pacific Ring of Fire and is most active in terms of earthquakes in the entire world. So Japan has approximately 20% of the earthquakes around the world of magnitude 6 or above. In 1 year, it has 1,500 earthquakes, and nearly every day there is a tremor. And you can see this from any little search online. The graph I show here it's about how long this shows, how long in between two earthquakes. As you could see, they are higher heights in between. So the time in between two earthquakes used to be a bit longer, up to 2011, the March 11, 2011, when was the so-called Great East Japan earthquake. And after that earthquake, one could notice that there are more frequent the time in between. So this earthquakes has shortened, something has moved. And how this affects, how this affects houses, how this affects property insurance. So at the moment, there is no insurance for earthquake in Japan for whatever reasons. One might being that earthquake, it's still considered an extreme event, which usually means rare, but in this case, it's not anymore given its frequency. The other one being that Japanese do not seem to tend to buy earthquake insurance. However, there are areas recognized as more prone to earthquakes than others. And usually immediately after an earthquake, the price of houses in that area would drop. Now, what happens in Japan is the so-called double debt problem, that when someone takes a loan or mortgage to buy a house, if that house is destroyed by an earthquake, after the earthquake, they still have to pay back the mortgage for the house they don't have anymore, and at the same time take a new mortgage for a new house. So that's why the double debt. So what we are suggesting in a joint work with Jiro Akahori and Yuri Mamura from Japan and Hai Ha Pham from Vietnam is that banks will, when they give out a loan for a mortgage, in the repayment of the loan, they incorporate a very small premium for the case of an earthquake, so that if someone loses their house due to this earthquake, they will forgive, they will not have to pay back the house anymore. So they can just take a new loan for a new house. So I hope these were just 3 simple examples of questions that you can see in actuarial mathematics. Now, the mathematics behind them, could be quite sophisticated, and it's a mixture of data analysis and stochastic modeling, and it evolves the results and the abilities for us to get better and more appropriate solutions it evolves at the same time with the evolution of the theoretical part of mathematics. Now, why I encourage anyone to study mathematics, and here in the picture, these are students from University of Liverpool going from Liverpool to London to present some of their results from summer projects. I think you have the opportunity to learn a lot, to make friends, as I said, to question what's happening around you and in the world. You can always find creative solutions to current problems, and you will be able to ignore the boundaries of societies and countries and just be a citizen of the world. Here is my email address. If you have any questions that you cannot ask me right now, I will be happy to answer them. Thank you.
Thank you so much, Dr. Constantinescu. If you have any questions, just drop them in the chat. If you're watching on YouTube, you can put your questions in there too. I am looking right now, so ask away.
Before I fall asleep.
Yeah. I have a question for you. Did you ever consider like pursuing any other subject besides math?
Oh, well, yes. My parents wanted me to be a medical doctor. So I was actually very fond of chemistry at the time. But nevertheless, mathematics was, or solving math problems was what really attracted me and made me relax. So I would take a break from preparing for the medical school by solving math problems. So it was a day when I thought, oh, well, maybe I should pursue mathematics and don't force myself anymore.
Awesome.
I have a question. So what would you recommend like high schoolers who want to pursue mathematics? Or what should they start doing so that they have the best way to go through their education? And like what could be something that can guide them through, at least in high school? What should they be doing?
I think they should just try to solve problems, any math problems they can encounter. And as I said, try to solve problems with some of their colleagues and friends and challenge each other and go to any competitions available. I think once you start to, there is a moment, you can be born with that passion, but there is a moment where you become very passionate about getting the right solution or solving a problem differently. And I think that's when you became a mathematician, when you think, oh, can I do it differently or in a simpler way? So probably that would be the advice. Don't be happy with the first solution you found to a problem. Don't be happy that you just did your homework. Try to do it differently. And again, try to compete with your colleagues. I think you learn more from your peers than from any class, any teacher, and any course. Well, I'm a living proof of that.
We actually still have 10 minutes, so
don't
feel yeah, don't feel shy.
I was trying not to include any of the models to stick to the stories. Is anyone in the audience that likes mathematics or wants to become a mathematician? You can react with your...
I have another question. So like in mathematics, let's say you are going into in university, you're majoring in math, right? What are the different um things you can do with it? Like I know, like you can go into finance, you can go into like where do you think is can these skills be used in the different fields that are there, or like what can a mathematician actually do after college exactly? Right? Kind of can you elaborate a little bit on that?
What kind of professions you can have as a mathematician? That's the
Yeah.
question.
Yeah,
Okay.
like yeah, that's kind
Apart
of the
from a
question.
ballerina, I think anything. So I think mathematics prepares you for a multitude of jobs. Now, of course, you can stay in education in academia or high school. You can become a teacher, which is always very rewarding. You can be an actuary, as I mentioned. So you can work in any institution that has to deal with risk and any institution that has to deal with data, which is basically almost everything nowadays. Um, and from my experience working with students, our students are very thought out because mathematics gives you a structured way of thinking, and it helps you pose the right questions, the correct question in a situation. Even if you don't have a solution, a perfect solution, having the right question is already a huge plus. And so, yeah, I cannot speak highly enough for mathematics. Of course, if you feel passionate about physics, chemistry, everything that is more experimental, even for those subjects, you still need mathematics. You won't have to go into learning new theories and writing new theories, but you'll still have to have a sound mathematical background. Even as a medical doctor, you have to know how much you should give, what is the dosage of in a certain, it's not, I think mathematics is actually beautiful. So it's and not difficult. It's I have a comment on the chat that Einstein didn't get far without differential geometry from his friends. Different times. Yes, I think you have to aspire very high when it comes to, regardless what you want to do. I like to see, and that's the reason I chose the examples and the stories I chose. We have other projects, but these are having societal implications, something that you observe in different societies, in different countries, and you begin to wonder if you can make any change, make any difference in this, and you can, but it's a matter of aspiration and courage to ask the questions, and you can do it. There is no limit.
Okay, well then I have another question.
Thank
Is there is there a like when you were studying mathematics, is there someone you looked up to, or was there, how did professors like help you? How did you kind of, yeah, who did you look up to as a mathematician?
you. So I looked up to my peers always. And again, I will repeat, it's not the same for everyone. I never had a big name mathematician as my role model. My role models were in my immediate reach, were my friends. I was always fascinated that they could solve a problem faster, or how they thought. And this helped me a lot. Now, not to say that were a lot of professors and teachers in my life that helped me become a mathematician. You know the expression that it takes a village to raise a child. I think it takes a village to to raise a mathematician. I'm sure there are mathematicians that are independent thinker and that they can do everything themselves. I'm not one of them. I learn best with others and from others, and sharing what I understand with others. So saying all that, I have to give all the credit to our high school and primary school teachers. So I'm originally from Romania, and we have like a math club where people would volunteer to teach us and solve exceptional problems. So, and they were doing this in their spare time. And I don't think we can ever repay them for that, either by being successful, but what they did is fantastic, and it's hard to replicate. But by doing that, they also encourage us to challenge each other. So they brought us together and gave us a problem, and we had to solve them, and that's how everything started. And I think this model, I cannot advocate enough for such a model to be developed in other places and other countries.
Oh, someone just asked, how long did it take to get your PhD?
Oh, yes. So I did my master and PhD at Oregon State, and both of them took 6 years. So together. So the first, I got my master's after 3 years and PhD after 3. Because it's the first 2 years are usually of grad school are a lot of classes. What made me choose, someone asked me what made me choose actuarial mathematics. I think what made me choose actuarial mathematics was the fact that the problems were concrete, were problems from the real world. I love mathematics. I'm sure you'll hear in the next talks about algebra and combinatorics and probability. So what they call sometimes pure mathematics, the blue sky mathematics, where you solve a problem, a beautiful mathematical problem that you do not know immediately if it will have an application. Where I think in actuarial mathematics, you go the other way. You have a real question and you try to formalize it mathematically. And then the answer may solve a real problem. So that made me choose it. Okay, so I have a question now. You have experience learning math in Europe and US. What do you see how we can view and learn math differently in US compared with the rest of world and Europe? Okay, so I've been, it's a very difficult question, complex question. So even within Europe, it's not the same. It's not taught the same. It's not approached the same. So for instance, Eastern Europe versus France, Germany, UK, Italy, every country has a very different approach to mathematics. So what I have seen as being successful is if you start very early, if you do mathematics and not shyly, not just a little bit, if you have the courage to study mathematics early on, take that advanced calculus class early on. Do not wait until college. These people will succeed. And this in other countries is compulsory. So what I've seen differently when I went from Romania to US was how more equipped I was from my high school and undergraduate studies theoretically, in terms of theoretical mathematics, than students coming from other backgrounds. And this was just because the syllabus on these countries was different. Of course, if you are talented and dedicated, you can overcome this difference, but it's easier if it's fed to you early on and you challenge yourself early on.
Thank you so much. So does anyone have any last questions before we move on? Okay, yeah. So
Thank you so much, Dr.
Yeah,
Konstantinescu.
thank you for your time. Continuing with our math guest speakers, we have Dr. Nitu Kishlu, a professor and chair of mathematics at Johns Hopkins University. He was first an assistant professor at Johns Hopkins before moving to the University of California, San Diego as an associate professor in 2004. In 2010, he returned to Johns Hopkins as a professor. Today, he will speak to us on the close relationship between algebra and geometry by offering an instance of how algebraic number systems bear a close relationship with certain higher dimensional geometric objects. So without further ado, please welcome Dr. Nitu Kishlu.
Thank you. Thanks, Catherine. Can you hear me?
Yes.
Excellent. So I just caught the last few minutes of your previous speaker. Beautiful words. I wish I had heard the whole thing. Wanted to thank her for her words. So I am one of the blue sky mathematicians, like she put it. I'm a pure mathematician. So in my area of expertise is topology, which is a variation of geometry. And I rarely get to talk to people in this age group, middle, high school. So I'm going to grab this opportunity and make the best of my time. I'm going to share my screen in a minute, but before I share my screen, I wanted to say the math I do, is abstract, like the previous speaker said. And I often get the question, what is research in math? What exactly do you do? I mean, do you create new numbers? What does it mean to do research in math? So I'm going to answer that question and give you some more of an idea of the kind of math we do in the pure subject and how it talks to nature around us. So I'm going to start sharing my screen, and let me know if you can actually see my screen. Give me a second. Let me just. All right. Do I have the authority to share the screen?
You should.
Give me 1 second. There it is. Okay.
Yeah, we can see it.
See this? Excellent. Okay. All right. So let me start off. I changed the topic just slightly. It's called Algebra, Geometry, and the World Around Us. Basically the same thing. The content remains the same. Okay. Did you see this now? Do you see the page changing?
Yeah.
Yes.
Okay, excellent. So like I said, the question I was often asked, so what is mathematics good for? What is it that you do? What's research like? So let's start off right from the basics. Of course, we all know that what mathematics is that it offers a framework, right? I mean, you get to count things, keep track of things, and the obvious thing that keeps track of these kinds of transactions is the real numbers. I'm going to call the letter R, the script letter R, for real numbers. And what it does, it, like I said, keeps track of information. You could solve the equations, look for solutions of the equations in the real numbers. But you come across oftentimes equations like this, right? I mean, it looks like a perfectly naive equation, x squared plus 1 equals 0. I've written it. We all know what it is, or we've probably seen it in high school. But we try to solve it and we run into problems because the answer to this equation, as some of you might know, is not a real number. So you're forced to introduce numbers which are no longer real numbers. We call them imaginary numbers. Okay. So here we have an imaginary number. I'm going to call it I, just for a lack of a better letter. We'll just call it I. And it stands for the square root of -1. And we all know that there is no real number that squares to -1. So I need to come up with a new number. I'm going to call it I. So this has been around for a very long time. And what it does is it creates a new collection of numbers called complex numbers. And complex numbers are just basically this number I that we've just created added to the usual real numbers. And then you take sums of things like that. So real number plus I times another real number, and you get what's called a complex number. And they behave just like real numbers do. You can add them, you can multiply them, subtract and divide. So the world behaves pretty much like it did with real numbers, except we now have this number we call I, which is the square root of -1. Okay, complex numbers are not just abstract objects. They are everywhere. They're to be found everywhere. If you will end up doing electrical engineering or other branches of engineering later on, you'll notice that without complex numbers, you have a huge handicap. You can't really do the subject you're interested in without the use of complex numbers. If you end up doing physics and you dabble with quantum mechanics, you'll realize that quantum mechanics is written in the language of complex numbers. You can't even start saying the things you want to say without having complex numbers available to you. And so you realize quickly that complex numbers make the world accessible to you. Okay, all right. So we have R, the real numbers, we have the complex numbers. What else is out there, right? Are there other number systems? Like, can you add, subtract, multiply, and divide with other things beyond the real numbers and the complex numbers? Okay, so this has been a question, or rather, I should say, there had been a question open for a very, very long time, right? People had been thinking about this. They had been breaking their head against the wall, trying to figure out, is there something you could do? Can you throw in some more variables and call them something so that you create numbers beyond the complex numbers? And the answer to that came to somebody in 1843, and his name was Sir Rowan Hamilton. Okay, he was an Irish mathematician, very famous guy. In 1843, he came up with a certain collection of equations. And the thing about these equations is that he was on a walk. He was walking, he was taking an evening walk somewhere in Ireland, and it hit him. The equations just hit him, and he was afraid he'd forget them by the time he got home. So what he did was, as he was walking over a bridge somewhere in Ireland, and the equations came to him, in a flash of genius, and he felt he'd forget them by the time he got home, so he etched them on the stone. So this is the bridge, actual bridge where it happened, and there's a little plaque over here. I know you can't read it because I can't either. I'm going to zoom into it, okay? So here's what it says. And if you still can't read it, I'll read it out for you. It says the following. It says, here, as he walked by on the 16th of October, 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for the quaternion multiplication. And then there's that formula for the multiplication, and it says, and cut it on a stone of this bridge. And if you want to know what these equations are that create numbers beyond the complex numbers, here it is. We'll call this letter H, this script H, to stand for the quaternions, which goes one step beyond the complex numbers. So you see here, you have the real numbers, you have the I that we talked about before. Now there are two other things. We'll call them J and K. And then the ABCDs are just, real numbers. So you could think of a number like 1 plus 2I plus 3J plus 4K. Now, J and K are new, and they behave just like I did in that they all square to -1, but they have this interesting relationship with each other that when you multiply I times J times K, you get -1. Okay, so everybody got interested and excited about this. And in that same year, they came up with octonions. In fact, the person who came up with octonion was a good friend of Hamilton. And octonions, instead of having 4 terms here, the number 1, the number I, the number J, and number K, it had, in fact, 8 such new identities. And I'm going to stop calling them by letters of the alphabet. I'll just call them E1, E2, E3, up to E7, okay? Just because, if we start getting more variables than 26, I'll run into trouble with letters of the English alphabet. So I'm going to call it E1, E2, up to E7. And these are all numbers, just like the imaginary number I. They all square to -1. But then they have this interesting relationship with each other, just like I, J, and K did with the quaternions. Okay, so now everybody's on a roll here. You have real numbers, you have complex numbers, you have the quaternions. and now you have the octonions. So remember, 1, 2 terms, 4 terms in the quaternions, 8 terms in the octonions. So you ask yourself, okay, we're getting stuff. Should we be investing all this thought into it? What is the point of all this? Like, where are we going with this? What exactly are these number systems worth? Okay, so they're certainly worth 48 cents. Okay, here's a stamp that commemorates Sir William Hamilton, and it says, here are the equations. I squared plus j squared, I'm sorry, I squared equals j squared equals k squared equals -1. And here's what he looked like. Of course, he did a lot more mathematics, and there in the background is some of the other stuff he did. And so now, of course, in seriousness, what exactly are these things worth? So we talked about how complex numbers were really important when it came to quantum mechanics. It turns out that these number systems are, in fact, incredibly important to physicists because they allow you to constrain physics of the world around us. In other words, what I mean to say is, if you want to come up with equations that describe nature around us, like physics beyond quantum mechanics, it turns out that what you really need are these number systems to understand the physics beyond quantum mechanics in more detail. So it's really palpable that these things have an important role to play in nature around us. Okay, so I want you to bear in mind that these things are not just abstract objects out there, they have some real meaning, physical meaning. Okay, so like I said, we have the real numbers. We call them by this R. There's the complex numbers, the quaternions and octonions. And the real numbers, of course, have one parameter. We'll call that 1, and then you can get any real number by multiplying 1 with any other number. And then the complex numbers had 2 parameters, the 1 and the I, and so on. Okay, so are there others? Okay, so what I want to do now, the rest of this talk, is to motivate the fact that this question, which is clearly an algebra question, cannot be answered using algebra alone. You need to start talking about geometry to answer this question. And now that's a bizarre aspect, right? Bizarre prospect of trying to answer a question in algebra using geometry. So, but I'm going to attempt to do that and show you what kind of objects show up in answering this interesting question in algebra using geometry. Okay, so I'm going to remind you of some basic shapes. Okay, shapes you've seen before. Let's talk about the circle. Okay, for reasons that'll become clear later, I'm going to call the circle s raised to a 1. Okay, this is not like a number raised to a power or anything. It's just notation. S1 stands for circle, and we all know how you write the equation of a circle. It's written as x0 squared plus x1 squared equals 1. Again, I'm using variables x0 and x1 because soon you'll see I'll start running out of variables, so I better start indexing them with numbers. Instead of saying x squared plus y squared equals 1, I'm going to call it x0 squared plus x1 squared equals 1. The thing to bear in mind is there are 2 variables, x0 and x1, playing the roles of x and y, and the sum of their squares equals 1. Okay, so that's your circle. There is the sphere, which you might also be aware of. Its equation has 3 variables now, and the sum of their squares again equals 1. So the sphere, I'm going to write it as S2 here, is made up of 3 variables, x0, x0, x1, x2, and x0 squared plus x1 squared plus x2 squared equals 1. Okay, so you see where this is going, right? I'm going to talk about the n-dimensional sphere. I'm going to write it as Sn. I'm going to define it using n plus 1 variables. Okay, n is any number here. Up to now, we've been talking about n being 2, up to 1 and 2, But now, I'm sorry, n being 0 and 1. Now I'm going to talk about n being arbitrary, any number. So Sn has n plus 1 variables, and its equation is given by x0 squared plus x1 squared all the way up to xn squared equals 1. Now, if you are like me, you'll have a hard time imagining this the moment n becomes, say, bigger than 2, right? Because we don't see in high dimensions. However, the equation makes perfect sense, right? x0 squared, x2 squared, xn squared equals 1. I mean, if you can find these many numbers that satisfy the equation, well, that's a point on Sn. So algebraically, if you set aside the fact you can't visualize it, this object makes perfect sense, and it sits in a nice sequence of objects, right? S1, S2, S3, and so forth. We can't picture S3 onwards, but there's no reason to stop there. The math doesn't ask you to stop there. It's a very interesting, easy, and continuous sequence of objects. Okay. All right. This Sn is an example of an interesting object a geometer would call an n-dimensional manifold. So bear with me, I'm going to explain what this is, and I think I'm attempting something that's probably not a very easy thing to do, but just bear with me here. So an n-dimensional manifold, what is an n-dimensional manifold? An n-dimensional manifold is a collection of equations like we just saw for Sn, so that around every point you have n directions to move in. So here's your S2. I'm drawing a picture of S2. And if you're sitting at this point and you're a little tiny creature, right, sitting at this point, what do you see? You just see a plane. You see two directions to move in, right? You have this plane on the surface of your S2, and you have two directions to move in. And that plane that you see is called the tangent plane. And of course, there's a tangent plane at every point on your two-dimensional sphere. There's one here, and there's one everywhere. Right? That's called the tangent plane. Okay, so like I said, if you were a tiny creature sitting on this n-dimensional manifold, you would see n different directions that you could drive your car in. For example, if you had a car and you had to drive at any point, you would have n directions that you could drive in, if you, of course, were to live on this n-dimensional manifold. Okay, here's the question. That's the motivating question here. Can you give someone living on Sn consistent driving directions at every point? So what do I mean by this question? So let's start off with an example. If you lived on a circle, you could tell somebody, okay, go clockwise 30 degrees or go negative 10 degrees. Well, negative 10 degrees simply means go counterclockwise 10 degrees, right? So that's a consistent driving direction to anybody living on the circle. You can tell them at any point, go 30 degrees or 10 degrees or minus 10 degrees, and they would understand perfectly what you mean, and life would be fine, and they would drive to wherever they need to drive to, given your directions. Okay, what about if you lived on the two-dimensional sphere? But we do, right? We live on the two-dimensional sphere. The surface of the Earth is two-dimensional. Here are some driving directions, okay, here. So the red arrow points south, and the green arrow here is pointing east, and these are driving directions. Everything looks great, except when you hit the poles, right? So say you and your friend start driving, and you decided you're going to, well, maybe not driving. Say you started to travel, and you decided you're both going to go to the South Pole. You start from the US, and your friend starts from Europe, and you both decide to meet in the South Pole, and both of you go due south, right? Both of you meet at the South Pole, everything's great, except when you try to compare what south means, it means completely different things. In fact, there is no south at the South Pole, right? What does it mean to drive south? And if you're coming from different directions, the direction you've been calling south is very different from the direction your friend has been calling south, right? You can think about it. Going this way and this way is very different when you meet at the South Pole. So these are inconsistent driving directions at the South Pole. In fact, it turns out for the two-dimensional sphere, there's going to be at least one point where your directions become inconsistent. Okay, here's a very big result in the field. There's a mathematician who is no longer alive anymore. His name was Frank Adams. And in 1960, he proved this very beautiful theorem in geometry. And he said that the only spheres on which you can have consistent driving directions are the one-dimensional and the three-dimensional and the seven-dimensional sphere, and none others, okay? Now, I want you to compare that with the fact that we had the complex numbers, the quaternions, and the octonions in dimensions 2, 4, and 8, right? So the question you ask is this a complete coincidence that the numbers 2, 4, and 8 are just one off from 1, 3, and 7? Okay, and it is not. It's not a coincidence. Here's why. So let's make believe you had a number system, right? Something beyond the complex numbers of the octonions, where you could multiply, divide, add, and subtract. And let's say it had n plus 1 variables, some hypothetical number n out there, and we'll call them a plus e1, a1, and all the way up to en, where e's now are playing the role of this imaginary number I, and they had some interesting relationship with each other. Okay, so you want to create driving directions on the n-dimensional sphere using this number system, and here's what you could do, right? Start with a number 1. There's a number 1 where all of these variables are 0 and just a is number 1, right? That's the real part of this number system. It's right here, okay? So if you lived on this n-dimensional sphere, at the point 1, you had n degrees of n directions you could drive in, right? Because if you see a plane, you see an n-dimensional plane, you have n directions. So what you do is you come up with a driving decision on that plane. You decide what's this direction, what's that direction, and you set yourself up with a template for n different directions. And now all you need to do to define what it means to drive in other directions at any given point is multiply the number 1 with that number to get you to that point. In other words, since you can multiply any number with 1, you just figure out your driving directions at 1, multiply the driving directions, and all of a sudden you have driving directions at that point. So what you've done is you've created consistent driving directions on the entire sphere using driving directions at only one point. And of course, the crucial fact here is that you could multiply numbers together, which you couldn't do unless you have this number system, which we are assuming we do. So what that tells us, if you use Adam's result, is that this cannot happen unless n is 1, 3, or 7. And so what have you just realized? You've realized number systems cannot exist beyond the octonion. So this is an amazing result that you have just come across using geometry. And it answers the question you started off with, is there any number system beyond the octonions? But there's more. What we just realized is that geometry and algebra talk to each other. They talk to each other in the background. You would not have expected it, but they do. But you also realized that the mathematics, the geometry and the algebra that you were just talking about, it tells you something about physics. In other words, it tells you you can't have physics that requires number systems beyond at 8 variables, beyond the octonions. In other words, physics is constrained by what the number systems allow us to do. So another way to say what I'm just saying is that nature listens to what math has to say. Why would this ever be the case, right? Math, of course, is something we create. Like numbers were not written in the stars, right? We came up and discovered, or rather, should I say, invented numbers, 1, 2, 3. Nowhere in nature were the numbers written down until we came around. So the things we create and we call math, why should nature listen to it? Okay, so this is not something I can answer in 20 minutes or half an hour. In fact, it takes people a lifetime to answer a question like this. And it indicates that there is something humongous going on under the surface here that suggests there's an interplay between math and physics that you wouldn't have expected, right? And that's what pure math is about. It's about exploring that relationship that lies under the surface. And then you see ramifications. You see things that happen on the surface, like electrical engineering, quantum mechanics, beyond quantum mechanics and physics. But under the surface is this beautiful song that's going on, and your job is to try and hear that. So that's what we do. Thank you very much. I will stop right here and entertain questions if you have any.
Thank you so much, Dr. Takicha. Let's see if there's any questions on the YouTube.
So when you go from like the reals to the complex, you're losing you'll lose order. So when you go from the complex to like the quaternions and the octonions, do you also is there an element that you're losing in that?
Could you repeat? You lose order, did you say?
Yeah.
Can you explain what that means? Lose order? I'm not sure I understand.
Like when you have the real numbers, you can order them, right? But
I see what you mean.
Yeah.
And so it's just that yes, you're right. You can't order them. Complex numbers, you can't order them in the naive way that the real numbers can be ordered. But that doesn't really play any crucial role, because the issue of driving directions is about n independent directions, right? So you take the one direction given by, let's say, along the real line. So say that's east-west. And then you're interested in the other direction being north-south. That is along the imaginary line. And then continue in that form for the octonions, you'll have 8 different driving directions. And so those directions stay independent of each other. So the order that you lose, as you say, doesn't really play any crucial role in the question we're asking. I mean, it may play a role in other things that are sort of tangential to this question, but the question makes sense without having to invoke order on the entire thing.
Oh, there's a question in the chat, if you see.
Could you, I have my screen.
Oh,
now.
yeah.
Could you just read it out?
Yeah. Have you watched 3 Blue, 1 Brown's video series on quaternions? He does a great job of helping one visualize them.
Yeah, I love Grant. My son and I have been watching him for a long time now, and we are sponsors of his. And yes, he's a genius, like my own math advisor said. Wonderful, wonderful job. He does a great job clarifying the concepts, and it's clear that he understands them thoroughly before he even attempts to explain it to others. Beautiful job. Incidentally, I had something here that I wanted to show you. If you ever were wondering, what is a two-dimensional manifold where you can have consistent driving directions? Here's the one. Can you see this? Can you folks see the donut?
Yeah.
Great.
Yeah, sorry.
So if we lived on a donut, we'd have no problem driving. Just the problem we had on the Earth, right, on the two-dimensional sphere, would disappear if the Earth was a donut. You see what I've drawn here are the consistent driving directions.
Someone asked, can a coconut be combed without a singularity?
Yes, it cannot. It's related to this question, but not. It's not exactly the same. It's a weaker version of this result of atoms. It's so let me repeat the question. So it's the question is, if I had a ball and I had hair on that ball, so like think of a coconut with hair on it, and I were to comb that hair, would there be a bald spot? Would there be a spot where the hair would have to either disappear or get into one of those cowlets? And the answer is yes, there would have to be a spot. And this goes by the colloquial name for this result is called the hairy ball theorem. And it's related to what I just said about inconsistent driving directions, but it's one step weaker than that statement. So in other words, it's much easier to prove the hairy ball theorem, much harder to prove the result that Adams proved. But they are sort of they're related to each other. I now notice that there are 13 questions in chat. Okay. All right, I think I've answered most of them.
And do you have any advice for high schoolers who want to go into math?
Well, your previous speaker did a fantastic job giving great advice. Get into math. The sooner you do it, the better, because you're going to have to learn so many other things as time goes by. Math turns out to be one of those things, if you are going into STEM, you're going to need math. You're just going to need math. There's no way around it in anything you do. And the sooner you get comfortable with it, the better it is. It gives you time to understand the basic concepts in the other areas. It saves you time in trying to understand concepts in math. As I realized from pushing my son, probably something I shouldn't do, but just to see how much a 9 or 10-year-old can fathom at an early age, it turns out kids, very young kids, can grasp pretty abstract concepts. So don't traumatize yourself or your little brother or sister, but try introducing them to abstract concepts early, and take the initiative yourself. And I think STEM enrichment is a great initiative, and I think you guys are doing a great job. The more people you can round up, the better it is. Start early, teach each other. Learning from others is a great way to do it. You could sit with a book, spend hours learning, but why not outsource that job? Have somebody else spend the hours and hours trying to understand a hard concept and then explain it to you. That's how math works, really. That's how collaboration works. Start early, get other people in the group, and keep the interest going.
Oh, someone asked, can you explain the difference between the algebra that we learn in high school and the algebra that pure mathematicians do?
Ooh, night and day, night and day. Okay. Well, okay, how do I answer this? You need the algebra you learn in school to do to do the basic work you do in life, right? I mean, you need algebra to keep track of your finances. You need algebra to basically, you know, buy your groceries, keep track of your monthly bills. That's the basic stuff. Now, pure mathematicians don't do it for the reason of application, right? They do it to understand what's going on. What's the relationship between the math and nature? They want to know, maybe I should explain it this way. You learn a language to read books in the newspaper and you know, just be literate. But you could learn the language to understand the language for its own sake. Mathematicians try to learn the subject for its own sake. They're trying to understand, how does this whole subject hang together? When you say, you know, there are numbers out there, why should the existence of numbers imply the existence of prime numbers, right? When we started learning about numbers, nobody told us there were prime numbers. They told us there's a number 0, there's a number 1, and so on. And at the end of the day, we could factor numbers, and then lo and behold, prime numbers showed up without being invited. They just showed up, they dropped from the sky. Why should that have happened? Why should the rules that we imposed that did not mention the word prime number end up resulting in an object called a prime number? What is the structure that governs the nature of things we do in the background? That's what a mathematician cares about. In high school, we learned the toolkit, right? We learn how to use algebra to lead our lives, and that's important, but that's very different from what a mathematician is motivated by.
Thank you so much. Are there any last questions before we move on? Okay, once again, thank you so much, Dr. Kishlu.
Thank you.
And we will be moving on to our next speaker. Our next speaker is Corinne Yap. She is a PhD student at Rutgers University doing research in probabilistic combinatorics. She received a BA in mathematics and theater from Sarah Lawrence College, and she studied math in Budapest and theater in Moscow. In 2016, she first performed her original one-woman play called Uniform Convergence, and since then, Corinne has performed at over 15 venues, including the National Conference MAA Math Fest and Off-Broadway. Today, she will be discussing probabilistic combinatorics and mathematical theory. So yeah, without further ado, Corinne.
Thank you so much for that wonderful introduction, Catherine. And thank you, Dr. Kitchler, as well for, I was watching most of your talk on YouTube and just joined. And it's interesting you ended by talking about this interplay between algebra and geometry and the relationships between math and physics. And I'm going to kind of continue that theme and talk about the relationships between different areas, both within math and outside of math. So let me go ahead and start sharing my screen. Okay, let me see if I can make it full screen. Can you give me a thumbs up if you can see it, Catherine? Great, thanks. So the title of my talk is Crossing Disciplines, Probabilistic Combinatorics and Mathematical Theater. So I will talk about both of these things. I'm going to start by saying a little bit about what combinatorics is, which is a specific area of mathematics. And then I'll go into specifically what is probabilistic combinatorics, which is the area where I currently do research as a graduate student. And then we'll do a little bit of math. And at the very end, I'll discuss kind of how I came to study this area and a different aspect of my life that's mathematical theater. And I'll try and also keep track of the chat in case people have questions during the talk. Please feel free to stop me at any point if you have any questions. Okay, so first of all, what is combinatorics? I imagine that not everybody has heard of this word or knows what it means. Roughly, it's the study of discrete structures. So in the last talk, Dr. Kijel was talking about different number systems, like the real numbers and the complex numbers. So those are both examples of kind of continuous structures, because you can think of the real line, the set of real numbers, as being continuous. From the interval like 0 to 1, there are no gaps in the numbers between 0 and 1. Whereas when we're talking about a discrete structure, you can think about the integers instead. So you have 0, 1, 2, 3, and you have kind of gaps between them. So another thing, another name combinatorics goes by is discrete math. Some people think discrete math is kind of a broader area that includes words like graph theory and algorithms and computational complexity. It's very much related to computer science. But let me give you some specific examples of what problems we're interested in combinatorics. The three most common broad problems are counting, existence, and optimization. So counting is probably if you have encountered combinatorics anywhere in your life, you probably first learned about it through a counting problem. The sorts of problems that you might learn in like a pre-calculus class. How many 7-digit phone numbers are possible? What if none of them begin with 0? So to solve this problem, you think about like, okay, well, for each digit, I have 10 possibilities, 0 through 9, and I have 7 digits. So I should multiply 10 times 10 times 10 for each of the 7 digits. So my answer would be 10 to the 7th. And then what if none of them begin with 0? Then I have to think like, okay, for the first digit, I only have 9 possibilities, and for the rest, I have 10 possibilities. So in general, we're interested in these kind of basic counting problems. How many of something can we find? Existence problems are asking like, does a particular type of discrete structure exist? Can we say like, okay, we want this thing that has these nice properties. Can we construct it? So an example of a problem here is if you have a set of medical students, there's what's called the kind of national residency, matching program where each medical student gives a ranking for their preferences for hospitals that they want to be matched at for the residency. And then the hospitals also need to choose which students they're going to accept. So a question you might ask is, does there exist a good assignment of students to hospitals? And you can give a list of like qualities that you want to define good. And this is actually a pretty famous problem in combinatorics that's called the stable matching problem. But the algorithms that have been developed to solve this problem have this very specific application in this residency matching. And the last type of problem is optimization. So given a set of cities and highways between them, what's the shortest route that visits each city exactly once? So that's an example of this problem. Here, we're not just looking at any old route. We want to find out what is the best route. So another famous problem in this area is something called the traveling salesman problem. So that problem asks like, what's the shortest route that visits each city exactly once and ends where it started? And this is a famous example of something that's a very computationally difficult problem. So this is a brief overview of the types of things we're interested in within combinatorics. But in the pure math discipline, we look at problems that kind of have these applications, but we're not studying typically we're not studying the applications themselves. We're really studying like the structural properties that are underlying these problems. And then when we kind of can prove things about the more abstract structural concepts, then we say like, okay, we can take this result we've proven and apply that to this cool problem. So now let me go into, let me do a little bit of a deeper dive into one of these types of problems. Let me talk about an existence problem. So here's an example of an existence problem. Suppose you have a party where every pair of people is either friends or strangers. And let's just make this easy on ourselves. We're not going to consider like casual acquaintances or anything in between. We're either friends or you're strangers. How many people need to be at the party to guarantee that there are 3 who are all friends or 3 who are all strangers? So this is a problem that I want to model using a discrete structure. And the structure that I'll use is a pretty common one used for these types of problems called a graph. And it's not a graph that you learn about like, in calculus and algebra classes. In combinatorics, when we talk about graphs, we're talking about a set of nodes and edges connecting those pairs of nodes. And here, I'm going to have the nodes representing the people at the party, and I'm going to put an edge for each pair of people. So here's an example of a graph. So here I have a party with 5 people at it, A, B, C, D, and E. And I've just put an edge to denote, every single pair of people that's at the party. And I want to distinguish between which pairs are friends and which pairs are strangers. So in order to do that, I'm going to color my edges 2 different colors. I'm going to say that an edge is blue if it's between a pair of friends, and red if it's between a pair of strangers. So maybe my party looks like this. So A and B are friends, B and C are friends, or sorry, A and B are strangers, B and C are strangers, but A and C are friends. So now my original question about having a party and guaranteeing certain sets of friends or strangers at a party has become this purely mathematical question, which I can write in this way. How many nodes should there be to guarantee the existence of either a blue triangle or a red triangle? Right, the way that I've colored this, a blue triangle represents 3 people who are all friends, and a red triangle represents 3 people who are all strangers. So I've just rewritten my original question in terms of this graph that I've colored for you here. And as you can see, 5 isn't enough, because if you look at this coloring that I have, I don't have any red triangles or any blue triangles. You can check every single triangle, for instance, A, B, C, right? There's a red edge and there's a blue edge. And then B, D, E, there's 2 blue edges and a red edge. If I look at every single triangle, I'll see that none of them are all red or all blue. Okay, let me give you another example though. Here's a party with 6 people. And I've just, kind of arbitrarily assigned some blue edges and some red edges to denote friends and strangers. This one does have some red and blue triangles in it. That's one example. There are several others. For instance, FJH is a blue triangle. So it turns out here for this specific party, there is a set of 3 people who are all friends, and there's a set of all 3 people who are strangers. Was this a coincidence? Did I just kind of get lucky with the way that I colored the edges? It turns out the answer is no. 6 nodes suffice always. So what this theorem says is no matter how the 6 people arrive at the party, no matter how which one of them is friends and which pairs are strangers, if you have 6 people, there will always be either 3 who are friends or 3 who are strangers. So in other words, what that means is that in any coloring of this graph on 6 vertices, in any way that I assign the edges either red or blue, I will always get either a red triangle or a blue triangle, or both. But on the flip side, 5 isn't enough. So we saw in the previous picture that we can have a party of 5 people where no 3 are all friends or no 3 are all strangers. And this problem is kind of the foundations of an area in combinatorics called Ramsey theory, where the motivating question is, given a structure, some type of discrete structure, how large does it have to be to guarantee I get these kind of nice, organized substructures in them? So in this particular example, I'm looking at how big does my graph need to be? How many nodes do I need to have in order to guarantee these nice, what are called monochromatic structures? So all red or all blue. But graphs aren't the only things you can ask these questions about. You could also ask the same things about, sets of numbers, if you're coloring sets of numbers, or if you're familiar with what vectors are, vectors in a vector space. So there are all sorts of different objects that you could ask this type of question about. Okay, so this was an example of kind of a typical combinatorial problem. Let me now talk about what probabilistic combinatorics is. So what we do is we take the 3 types of problems, the counting, existence, and optimization, and we introduce randomness in some way. And why do we want to do that? Well, there are kind of 2 different ways that we like to introduce randomness. One is that we study random variants of discrete structures. So we take things that we study in combinatorics, like graphs or matrices or walks, and we put the word random in front of it. Random graphs, random matrices, random walks, and we study those objects instead. And why would we want to do this? Well, an example of a problem where you'd want to use a graph is if you're modeling social networks, right? Say you want to construct a graph that represents all of your friends on Facebook and all of their friends and all of their friends. You could have the nodes represent the people on Facebook and the edges represent, if you're friends or not. And if you want to say something, if you want to kind of simulate a typical social network and say something about what social networks look like in general, it might not be enough to just look at your personal social network, right? Because that could look a lot different from someone else's social network based on, how old you are, or how many people you know, or what types of things you're interested in. So in these types of problems, we instead want to study like random networks, because then we can say things like, on average, a social network might look like this. It might be this connected, or it might be this dense. So that's one way of kind of injecting probability into these types of problems is by just kind of looking at random variants of things. Another way is to study deterministic structures, so non-random structures, but use probability to find solutions. And I want to talk about this part a little bit more. So essentially what we do here is we translate the statement, there exists something, to the probability of something is greater than 0. And this is kind of a vague description, so let me give you a more specific example of what I mean here. So we're going to get into a little bit of math. So if you've seen probability before, some of this will look a little bit familiar to you, but if you have not seen any probability before, then don't worry too much about it. I will let you know which things you can kind of gloss over and not pay attention to. Okay, so let's go back to this party problem and change the numbers. How many people do we need to guarantee now that there are 10 at the party who are all friends, or 10 who are all strangers? That's a lot bigger than 3. Now we're looking at 10 people who are all connected by edges that are all the same color. And I just want to know, let's make a guess, 100. Is 100 people going to be enough? So to solve this, we want to look at a graph on 100 nodes now. Is there a way to color the edges red and blue so that no set of 10 people is monochromatic, which means they're all friends or all strangers? So if you were to do this in a way that we kind of tackled the earlier problem with just 5 nodes, then the sort of brute force way to do it would just be to run through all the possible ways to color this graph on 100 nodes. But there are going to be a lot of edges in that graph, and it's going to take a computer ages to run through all the possible colorings, and in each coloring, look for all the sets of 10 people and figure out if they're monochromatic. Because again, this is an existence problem. We want to prove that there exists a coloring where we don't have these monochromatic subsets in it. So in order to show something exists, then the kind of naive way to approach it would be just okay, let's find one. Let's find a coloring. So instead of trying to just brute force the problem, I'm going to try this clever idea of doing a random edge coloring. So for each pair of people, I'm going to flip a coin. And if the coin is heads, I'll color the edge red. If it's tails, I'll color it blue. And then I want to look at, okay, what edge coloring will I get out of flipping coins? Well, let's look at a specific set of 10 people. Let's ask, is it likely that they're going to be monochromatic, that they're all going to be friends just from flipping coins, or that they're all going to be strangers just from flipping these coins? So I want to calculate this probability. What's the probability that they're all friends? Well, I have 1/2 probability that my coin will land heads for each pair of friends. And there are 10 choose 2 pairs. So if you're familiar with this notation, then 10 choose 2 is something called a binomial coefficient. It represents the number of ways to pick 2 people out of 10 people. If you're not familiar with this, don't worry about it. It's just the number of edges that's among this set of 10 people. And I've calculated it out for you. It's 10 choose 2 is equal to 45. So there are 45 edges, and each of them needs to come up heads. So the probability that all of them come up heads is 1/2^45. Then I look at, what about if they're all strangers? Well, now each of my coins needs to come up tails. So again, I have the same probability. I have 1/2^45. So if I want to look at the probability that they're either all friends or all strangers, I just add these two together. And I say okay, the probability that this specific set of 10 people is monochromatic is 2 over 2 to the 45. Okay, so where is this going? Well, let's look at the total number of monochromatic 10 sets I have in my graph. So I have my random coloring, and I want to count how many 10 sets there are that's monochromatic. But this is a random graph, right? So I can't just like go in and count them, because anytime I run my experiment again, I'm going to get a different number, right? Anytime I do new coin flips, then X is going to change. So really what I want to know is, what's the average value of X? If I do my experiment a bunch of times, on average, how many monochromatic 10 sets can I expect? And so this is where, if you know probability, you might know where this expression comes from. The expected value of X is equal to this. If you don't know probability, I'll mainly just black box it. So 100 choose 10 represents the number of sets of 10 people there are in this graph. And I'm multiplying it by 2 over 2 to the 45, which is the probability that a specific 10 set is monochromatic. So that's just using this thing called linearity of expectation. I can add up a bunch of expected values. I won't go any more into it, since, you know, if you don't know probability, then this will just be a way I calculated expected value. And if I calculate this out, this ends up being about 0.49, which is less than 1. Okay. So why do we care about this? Well, this is where the Erdős magic happens. I mentioned this in my abstract that the probabilistic method is also called Erdős magic. This is an average. And since the average is less than 1, what do we know about averages? If you think about just like an average of a set of numbers, then the property, the meaning of it being average is that there's something that's at most the average, and there's something that's at least the average, right? Because you're thinking about it as kind of the middle. So what I've told you is that the average value of X is less than 1. And X has to be an integer. It's counting a number of sets. So that means that there is a coloring where X is at most the average, and there's a coloring where X is at least the average. But if there's a coloring where X is at most the average, and the average is less than 1, right? The biggest integer that's at most the average is 0. So by this property of averages, I can say that there's a coloring where X is equal to 0. But what is X? It was the total number of monochromatic 10 sets. So there's a coloring where the number of monochromatic 10 sets is 0. And now let's think back to what we wanted to show. Remember, we wanted to show that there exists a coloring where the number of monochromatic 10 sets is 0. We're 10 people, there aren't 10 people who are all friends or 10 people who are all strangers. So it turns out that 100 is not enough to guarantee that there are 10 who are all friends or 10 who are all strangers. So what happened here? We didn't construct a coloring. I can't hand you which coloring I'm talking about. I'm saying that there exists a coloring where no 10 people, there exists a party where for every set of 10 people, they're not all friends and they're not all strangers. But I haven't told you what this party looks like whatsoever. I've just told you that I know it exists somewhere out there in the ether. And so this is where I guess the magic part comes in. And it's called Erdős magic because it was coined, this method was formulated by a famous mathematician named Paul Erdős, who he was very prolific, and he's one of the most famous mathematicians, and particularly in combinatorics. So, let me take a look at the time. All right, great. So anyway, let me just say that there was nothing special about 100 or 10. So I can replace those numbers with variables to get a theorem, which just replaces the number 100 with n and the number 10 with k. And I have essentially given the same expression that I had for the expected value here and said, if this expression is true, then there is a way to color all the edges among n nodes so that no set of k nodes has all monochromatic edges. So this problem had nothing to do with probability, but by introducing randomness, we could use tools from probability to get a solution. So for me, the reason I study, the reason I became fascinated with this magical idea and with probabilistic combinatorics is we're taking two areas that don't really seem to have anything to do with each other, and we're using tools from one area to solve problems in a different area, right? If you looked at this problem, you wouldn't think that randomness would have anything to do with solving the problem, but somehow by imposing this random structure, we end up getting this really powerful and really sort of magical result. Okay, so in the few minutes that I have left, I want to, so that was a lot of math, so it's okay if you didn't totally follow everything. I want to pivot away from doing math and talk more about, my life with math, and the second part of the title, which was mathematical theater. So I talked about how I enjoy, kind of crossing disciplines within math, but I also want to talk about how I've used math in other areas of my life, and in particular, mathematical theater. So I have written and performed, as Catherine said in the introduction, a one-woman play called Uniform Convergence. And I have the synopsis here, but I'll summarize it. It's a one-woman play that's about the stories of two women. The first is of historical Russian mathematician Sofia Kovalevskaya. And she really faced a lot of, difficulties due to sexism in trying to really become, trying to get her name out in the math world at the time in late 1800s Russia. And the second is of a fictional Asian American woman known as the Professor. And she is teaching an introductory real analysis course and uses math concepts to draw parallels to race and gender conflicts she encounters in society. So I wanted to end by playing a clip, and then I'll say a little bit after the clip, but it's only a couple of minutes. I think that would be better than me trying to verbally describe the show. So let me share computer sound and play this clip.
Take the human life, for example. It's a continuous thing. It's impossible for life to be discontinuous because it only continues until you die, and it doesn't pick up again from where it left off. On this earth. But my life is most certainly non-uniformly continuous. If you let delta be some span of years, say from when I was 8 to when I was 15, in order for it to be uniformly continuous, then for any span of years or months or days between ages 8 and 15, you should be guaranteed to find a value which that time span is approaching. In a normal life, one could define that value as puberty, as 8th grade graduation, as acing next week's history test, any of the trivialities that we set as our goals for however long they're relevant. But for me, my trajectories are always interrupted. Never as simple as they initially seem. When I was 15, I wanted to be an actress. The next year I was cast in the school musical as a Chinese man named Chang. It's the melanin. It's the extra molecules of melanin in my blood that manifest themselves into these societal barriers, into the discontinuities, into the jagged lines and the rough edges that make every beautiful continuous function into a hideous conglomeration of edges and vertices. It's the straight black hair and the dark brown eyes that create these extremal points, these suprema and infima, the small stature and the last name that prevent every span of time from having a predictable endpoint. Because if you pick out an epsilon, I can't always give you back a delta. I fell in love with a blonde boy with green blue eyes whose laugh made me drunk on California sunshine. We stood side by side and the mirror told me that his skin was darker, but according to everyone else, I was the colored one. Let f be a function mapping the imaginary to the real. If x and y are points in my imaginary world that are so close together they look like they touch, then when are their analogous values in the real world close enough to occur with an epsilon equals the span of my life?
Guess I chose to end on a rather dramatic note. But since I'm almost out of time, I won't share my last slide, which is I'll just say it out loud. So that was a clip from my show. And the takeaway that, or I guess what I want to tell you about it is that math doesn't exist in a void, right? We bring, as mathematicians, we bring our identities, our perspectives, our experiences into the room when we do math. And for me, that was a really important realization that I had when I tried to merge these two interests that I had, math and theater, and didn't think that it was ever something that would happen. But, you know, the math community has been really accepting and supportive of this play, which I didn't realize at first. I wrote it before I entered grad school and kind of put it away for a while until I realized that it was something that my friends in graduate school and people at other departments were interested in. And it's led me to meet and have a lot of really wonderful people and have a lot of really amazing discussions about things that I really care about within the STEM community, which is diversity, which is making our departments and our classrooms more welcoming and creating a welcoming environment for students of all backgrounds. So that is to say, I encourage you to not forget about who you are and what you love, even if you do choose to pursue math, even if you decide that you want to major in math in college and go on to graduate school, or if you decide to go into industry, or if you don't do math at all. Just remember that math is a place where you can go and still be who you are and still have your other interests. And I would encourage you to pursue whatever it is that you're passionate about. So I think I'll end there. Thank you.
Thank you so much for sharing, Corinne. Does anyone have questions for her?
So I got a question in the chat. Have you used probabilistic combinatorics with computer science? So I haven't, but I have several colleagues who do. So in fact, in my kind of research group amongst graduate students, about half of us are pure math and half of us are computer science. And we do like reading seminars together and talk about papers. So yeah, it's not something that I have personally done, but there are a lot of people who dabble in both fields.
And there's another question in the chat asking what inspired you to write Uniform Convergence?
So I started writing it when I was a sophomore in college, and it started out as a history play for a playwriting class. And I was like, oh, this is my chance. I can write about a mathematician and finally like merge math and theater. So I started writing about Sofia Kovalevskaya, who has a really fascinating life. If you ever, need something to read, go look her up. But at the same time, I was taking a real analysis course, which is the course that is kind of the premise of the show. And there were a lot of things happening on my college campus that I felt really strongly about with regards to students of color and with regards to opportunities for students. And that inspired me to start writing this second character, the professor, kind of based on my own opinions and my own experiences. And over the years, it just sort of evolved from there. And at some point, these two characters kind of decided to coexist in the same world. And that's when Uniform Convergence happened.
And I had another question. Are you still performing this?
Well, not currently because of COVID. I had a few performances that were canceled at the end of the spring semester. But once we are back in person, I will be performing. I have a few performances, like every month or so. Yeah. So if you are at an academic institution, I performed at colleges and high school programs and all sorts. Feel free to invite me. I don't charge. I also have, if you are interested, I don't have a video publicly available because I don't have one that's like of high quality. I have some from just like various performances. So if you're interested, you can message me or email me. I think my information is I'm on the Slack site and I can send you a link.
Thank you so much. Are there any last questions before we move on? All right. So thank you so much, Corinne.
Thank you.
Yeah, and our next guest today is Dr. Tom Hull. He is an associate professor of mathematics at Western New England University, and he is considered a leading expert on origami mathematics. He received his PhD in graph theory from the University of Rhode Island, and he has written origami instruction books and research papers. His most popular origami creations are the fizz unit and the 5 intersecting tetrahedra model, which is voted by the British Origami Society as one of the top 10 origami models of all time. His talk today will be on origami in math, paper, polymers, and robots. So without further ado, please welcome Dr. Tom.
Hi, thanks, Catherine. And thanks for inviting me to this this event. This is kind of amazing what you're doing here. It's cool. So let me share my screen and get this started. So yes, I'm talking about origami and math, which is about, well, a lot of things. But before I start, I should point out that it is, I think, illegal to give a talk on origami without having people actually fold something. So we are going to do a little bit of that. It'll come up in a few minutes. If you have, all you need is a piece of paper and a pen, and it doesn't matter what shape piece of paper. I just have an 8.5 by 11. So if you can scrounge a small piece of paper, you'll be good to go. Having a pen is nice too. But anyway, yeah. So I just want to give an overview of something that's kind of like a passion in my life. I've been doing origami since I was 8 years old. I'm also a mathematician, and somewhere around college, grad school, they started coming together, and that was really kind of awesome for me. I got to take a hobby and turn it into a career in a sense, or merge it into my career as training to be a mathematician and a math professor. So I want to give you an overview of like what that's about. This animation you see, which is just an animated GIF, that's kind of like, well, you'll see. I'll talk more about that later. But just the fact that I can make this animated GIF that is simulating something called rigid origami is means there's like a lot of math to unpack just from something like that. So but first of all, what is origami? Most of you probably know, or hopefully you've folded something, or you might wouldn't be here. But yeah, paper folding. You're folding paper. It's a Japanese word. Ori means fold. Gami means paper, kind of. And normally, you fold things like cranes. That's what we see here, an origami crane. And if you unfold it, you get something called the crease pattern. And that is like a blueprint of the model. And that's where a lot of the math exists inside an origami model. The kind of basic question is like, how do you go back and forth between folded object and crease pattern? There's clearly a connection. In fact, I remember being at like 12 or 10 years old, folding models because they were fun, because I thought it was cool, and I really liked doing it. But somewhere around then, I unfolded. It might have even been this model, this classic crane model. I unfolded it and looked at the crease pattern and immediately thought, oh, look, it's math. There's certain angles, there's certain things going on here. And so that's kind of like maybe what started me thinking about the connection between origami and math. But I was 10, I didn't know what I was doing. But one thing that ends up being really important that we're going to talk about later is whenever you fold something, especially if you fold something flat like this crane, the creases come in two types. You have a mountain crease or a valley crease. And that tells you which direction they're going in. If you're looking at the paper from one side, some of the creases are coming up at you, making a mountain. Others are going away from you, making a valley. So more on that later, because there's some fun math there. But just to kind of give an overview, you got classic traditional origami. Some of you may have folded these models before. These origami pieces, as origami folds people have been doing them for hundreds of years. They go back to ancient Japan, like at least the 1600s or 1700s. No one really knows for sure, but classic Japanese crane, classic Japanese frog. Yeah, that's like ancient origami. More modern origami looks kind of crazy, but there's a lot of it, and you can find a lot of it on YouTube or by searching the internet for complex origami models. This is one of my favorite. It's made by a guy named Jung Maekawa, who is a Japanese physicist and an origami artist. It's his Demon. It's on the cover of this book called Viva Origami that was published in the 1980s. And this is the crease pattern for it. And it's way more complicated than the crease pattern I showed you before. But it's still, this is like one square piece of paper, no cuts, and you get all this detail. 5 fingers on each hand, a tail, legs, eyes, tongue. It's all here. It's all here somewhere in the paper. And studying complex origami is really kind of amazing. Here's another example of more modern origami. This is Satoshi Kamiya's wasp. And there are a lot of origami wasps out there, but this has got to be the most complicated one I've ever seen. Unlike My Cow Demon, where if you can find a copy of this book, or there's some other books that have this in it, if you Google My Cow Demon, you might find instructions online. There are instructions. You can fold this step by step, okay? This one, no, you can't. I mean, well, at least no one's tried writing down step-by-step instructions. If you want to fold this wasp, you got to, this is the instruction right here. You find this crease pattern online, and then you try to fold it. It's really, really, really hard. But the amount of detail is amazing. And you can find a lot of origami models that are kind of like this. This is a model called Attack of the Kraken by Brian Chen. I really like this. This is, again, one piece of paper. And you got the squid, you got this boat with sails and stuff, all one piece of paper. Here's the crease pattern. He decided to give it a Pirates of the Caribbean kind of look, which is kind of fun. But you know, this big, I don't know, like rhombus-like region, that's the sails, that makes the sails of the boat. Whereas I don't know if you can see where the Kraken goes, but well, the squid body is right over here. There, it says squid there, and there's the eye of the squid. And so it's like, it's amazing that you can do this. You know, the fact that you can like develop origami models that are this complicated is really kind of amazing. And it's no, you know, comparing like ancient origami to this more modern origami, the origami developing in complexity does go in parallel with our greater and greater understanding of the mathematics behind origami. That's not a coincidence. Okay. So to give you a feel for how understanding some of the math can help you with crease patterns like this, or crease patterns like Satoshi Kamiya's wasp, I'd like us to do an activity. Okay, so this is where the paper comes in. So if you have a piece of paper and you have a pen, the only reason why I suggest a pen is to draw a dot in the middle of your paper. So I'm going to do that. I have a piece of paper. I'm going to draw a dot on it. So I would like you to do that too, if you can. Okay, and here we're all going to discover an origami theorem together and then take a look at the proof. Okay. So take a piece of paper, draw a dot in the center, and then what I want you to do is make a crease going through your dot. Okay, so you want to look at your dot there and make a mountain crease. Okay, that just goes through your dot, and it could be anywhere. So make it at any angle, but you know, a straight crease going all the way through. You want to be able to see your dot though, so make it go through your dot. Okay, and then I want you to do that again. Leave it folded. Okay, leave your piece of paper folded, but then make another fold through your dot. And it could be a mountain or a valley, doesn't really matter. But you know, make it at some angle. I'm going to do mine like this, but yours might look different. You might make it look like that, but you know, you get to pick how this works. Okay, and you want to do that a couple of times. Okay, like you could stop here if you're satisfied with what you just did. You can stop there, or you can flip your paper over and do it again. Make another crease that has to always go through your dot though. Okay, and so do this a couple of times. You get to decide when you want to stop. Okay, so everyone's will look different. What we're doing is gathering data to make a conjecture that we're then going to prove. This is math. This is how we do math, right? Okay, so I'm going to stop here. You can do some more if you want. You want to make your creases sharp. Okay, so either use your fingernails or put it on the table and like rub your fingernails to make them sharp. Okay, because then what I want you to do is unfold this. Unfold your piece of paper and then look at your dot. And what I want you to do is, coming out of the dot, you will have mountains and valleys. And what I'd like you to do, and I'm going to actually stop sharing my screen because I want to make sure I turn on the chat, although I'm going to share a different screen actually, so that way I can keep track. I want people to tell me in the chat window how many mountain creases and how many valley creases you have coming out of your dot. Okay, so I'm going to try an experiment here. I'm going to share this screen so I can keep track of the numbers you share. And then I have to open the chat window. So again, you're coming out of the dot. Like I have 6 crease lines coming out of my dot, and some of them are mountains, some of them are valleys. If people could type in the chat window how many mountains you see, how many valleys you see, I will record them on here. And yeah. Oh, wait, I got to go down. I haven't. So no one's told me what they have yet. Or you can unmute your microphone and just tell me verbally if you're feeling brave. How many valleys, how many mountains? You can't really get this wrong unless you don't count properly. But okay, so someone says, oh, wait a minute. Someone says 4 mountains, 3 valleys. And someone else says 4 mountains, 4 valleys. Be careful. You want to, and someone says 7, 5. You're counting each crease coming out as different. So I have 6 creases coming out. So my total should be 6. Okay. So I don't think you can get 4 and 3. So you might want to recount 2 and 6. Some of these numbers don't make much sense to me. So I wonder if you're counting correctly. But someone got 7 and 5. That makes sense to me. 4 mountains, 2 valleys. Okay. Yeah, so you do have to count. So let's see, what do I have? Oh, I have 4 and 2 as well. I have, let's see, what do I have here? Here's a mountain, there's a mountain. I have 2 mountains there, 2 mountains there, and then 2 valleys. So the total is 6. 3 mountains, 5 valleys. Cool. Yeah. The thing is that there's something going on here. So, and then someone else got 7 and 5. I already have that down. Of course, if you turn your paper over, you could get all your numbers switched, right? 2 mountains, 8 valleys. I don't believe that. So whoever did that might want to count again. This is one thing, another easy thing to make mistakes is if your creases weren't sharp, it's easy to forget. Or if you made too many, 5 and 3. Well, that's kind of like 3 and 5 if you turned it over, but still, that's okay. So I'm curating the data slightly because I know what's supposed to work. But does anyone see the pattern in these numbers? I know there's at least a few people listening who already know the answer to this, but there is a pattern here. Can any of you see what it is? One thing that's interesting, yeah? I thought I heard someone.
They add up to an even number.
They add up to an even number. That is absolutely true. It's not what I was looking for, but it's absolutely true. You can prove that as long as you fold something like this flat, you know, that every vertex in your crease pattern, if you fold it flat, has to have an even number of creases coming out of it. That's definitely an origami theorem.
One is 2 more than the other.
Yeah, the difference of all these always seems to be 2. In fact, let me do another one quickly that it looks like all of you, none of you wanted to stop after just 2 folds, but even if you just did 2 folds, so you only have 4 creases, like here I have what? Mountain, mountain, valley, mountain. So another possibility is you can have 3 mountains and 1 valley. That's like one of the most simple things you can do. You know, but yeah, that is basically it. The difference between mountains and valleys is always 2 if you're folding something flat, doing what's called flat origami. Okay, so I'm going to go back to my slides because that origami theorem actually has a name, and it's and I'd like us to take a look at the proof because hey, that's what math is doing. Okay, so yeah, so this result is called Maekawa's theorem. It's named after the same person who made that demon, Jung Maekawa. And it basically says this: if you let V be a vertex in a flat origami crease pattern, and M and V be the number of mountains and valleys, then if you subtract them, you always get either plus or minus 2. And whether it's plus or minus depends on what side of the paper you're looking at, right? That's what's happening there. Okay, so there's a lot of ways to prove this, but I like doing a proof like this because this is the kind of thing where if you were to just try to sit down and prove it, like where do you start? This is very much applied math in a sense. Like we're taking something physical that we observed and a conjecture that we made about something physically folding a piece of paper, and now we're trying to prove that that's always true, but we don't have any machinery to start with, except we do. There's lots of math you can apply to these things because there's a little bit of geometry going on here. We're folding paper, but there's also some combinatorics. It's interesting. So here's one way you can approach this proof. And that is to do something you're not allowed to do in origami, and that is use scissors and cut off your vertex. So imagine, so here I have a little cartoon of a crease pattern with only 4 creases, but okay. And imagine all we know is that it folds flat. So we fold it flat, and then I imagine cutting the vertex off. Do that because I want to look at the cross section, which is actually a polygon if you think about it, but it's a flat polygon. So I can actually demonstrate. Let me demonstrate that with my piece of paper. Here's the one I fold. I'm going to cut off the corner there, and then what I have here is a polygon. If I open up the paper a little bit, you can see it. And I don't mean that this polygon. I want to leave it folded. Okay, so it's folded. And it's like some zigzag polygon. If I open up the paper a little bit, I'll actually have angles, but it's actually a flat polygon. But it's really the cross section. That's what I'm looking at. So here's what I want to do with that cross section. I want to do something that's called a proof by monorail, okay, which is a technique we use in origami for more than one theorem. So this is actually a thing. So this little picture I have here, that is supposed to be a monorail traveling along the cross section. That is not a purple finger with teal fingernail polish. It's supposed to be a monorail, and monorails travel along these tracks. They hit corners and turn, and they come back to where they started. So the question I have is, if we look at this cross section, so I'm looking at the cross section from above, and I'm imagining, you know, like this, and I'm imagining the monorail going back and forth along this flat polygon. Now, imagine some of these creases are mountains and others are valleys. So, so let's see if if every time I hit a mountain crease, I'm going to rotate by 180 degrees, okay? Because this is a flat polygon. And every time so if this is a mountain, I'm rotating by 180, and then I hit this mountain 180. But then this one in the middle, that's a valley crease. I'm going to rotate by negative 180 degrees, and then 180 degrees again. Then I'll come back to where I started, right? So every time I hit a mountain, I rotate by 180. Every time I hit a valley, I rotate the opposite direction by negative 180. And what I want to do is well, I come back to where I started. So the total rotation should be 360 degrees, because I'm just going around a circle and coming back. When I come back to where I started, the monorail will be in the same orientation as where it started. So this total rotation, 180m minus 180v, should be 360. And you know, just you divide by things, and there you go. M minus v is 2. And that was assuming that I had more mountains and valleys. If I flipped the paper over, I would have gotten -2. You know, so or v minus m equals 2. Yeah. So that's an origami theorem. And it's things like that that allow people to study origami design or do other things too. Okay, so so next I want to kind of go through quickly like various other types of math that are involved in origami. This Maekawa's theorem that we just saw, this is actually a combinatorial result. It's about counting mountains and valleys. It uses geometry in the proof a little bit, but it's really about counting things. Still, there is a lot of geometry in origami. When you fold paper, you can think of it as like doing a geometric construction. And I could do a whole talk on that. You can actually show that with origami, you can trisect angles. You can actually do more than you can with strategy and compass. That's a lot of fun. But it's like straight origami geometry. But there's other things too. And this is called Kawasaki's theorem, has to do with, is really important for origami design. And that's like, if you fold, again, if you have a flat folded vertex or a crease pattern that folds flat, and you look around any vertex and you look at the angles between the creases, this is a very much a geometric result. Then if you add up the opposite angles or every other angle, so here alpha 1 plus alpha 3, that's got to equal 180. Or alpha 2 plus alpha 4 has to be minus 180. Another way that people phrase that is if you take the alternating sum of the angles, alpha 1 minus alpha 2 plus alpha 3 minus alpha 4, and so on. It doesn't matter how many there are, the alternating sum will always be 0. That's actually equivalent to writing it as 180 degrees. But that's nice because this is actually an if and only if theorem. If this angle condition is true, then your vertex will fold flat. There's a way to go back and forth. So this is actually a very useful theorem about the geometry of flat origami crease patterns. Yeah. And another thing, this kind of ties in a little bit to what Corinne's talk was about. We can think of an origami crease pattern as a graph with vertices and edges. And one neat thing you can prove about this that has to do with what someone observed when we were doing our experiment is that if your crease pattern folds flat, every vertex will have an even number of creases coming out of it. Okay. And you can use that to prove that if you want to color the faces of your crease pattern, you can always do it with just 2 colors. There's a way to do that in graph theory, that if you have a graph and every vertex in its interior has even degree, has even number of edges coming out of it, then you can always 2-color it. But there's another way to prove this that's even more elementary. And that's that to imagine what would this look like? Like, remember, this is the crease pattern of that crane. What would this look like if I actually folded it up again? Well, I would love to spend time for you to think about it, but this is what happens. All of the white regions end up facing in one direction and the gray regions face in the other direction, which makes sense. everywhere there's a crease, you're folding in half, you're folding the paper flat, so the white will point in one direction, the gray will point in the other. So you get this neat thing where if you end up with your crane, but if you flip it over, it turns into the other color, which is kind of fun. If you know how to fold something like this, I highly encourage you actually try doing this. Fold something flat, unfold it, color it like this, and then fold it again. It's fun. It's really fun. What else can you do? Here's something that was surprising to me when I first encountered this. You can model origami with matrices. And this does make sense because you use matrices or matrix transformations to do geometric transformations in space. And this goes beyond flat origami. So this is a picture of a three-dimensional thing. This is called a corner of a cube. It's just, you have these 5 crease lines, and this makes a 3D vertex that folds into a corner of a cube. And you can model what the paper is doing along each crease with a rotation matrix. And you want to think of this as something that's telling you what is the paper doing if we were to rotate, say, by pi/2 radians or 90 degrees about, say, this crease line along the x-axis. Well, you would use this rotation matrix. I would put pi/2 into theta here. And that is something I could use to actually model it folding. The cool thing about that is that there's a nice theorem that says that as long as your paper doesn't tear or stretch, which is always the case with origami, then if you multiply all these rotation matrices together around a vertex, you should always get the identity matrix. And this is a way of combining linear algebra or matrix algebra with origami. What's great about this is that it is matrix products like this that allow us, that give us what we need to do animations like this. These are animations. I did them on Mathematica, and it's a computer simulating origami. There's no real actual folding happening here, but what these matrices allow me to do, and then there's this one, which no, I don't think I showed you that one before. What they allow me to do is figure out the folding angle relationships between all the creases. Okay, and that all comes from this one equation. All of these animations were done basically by exploiting this equation. And that's something that's actually been really interesting to engineers and physicists. But before I talk about that, I just have this slide of where I just try to make a list of different type areas of math that actually apply to origami. This is something that's been really exciting for me as a mathematician who loves to do origami. As I study more about the connections between math and origami, I'm continuously amazed at, you give me an area of math, there's probably some way for me to use it to study origami, or vice versa. There's maybe some way for me to use origami to study that part of math. Everything from, like I said, geometry, matrix algebra, combinatorics, and graph theory. You've already seen examples of that, but there's others. Statistical mechanics, which is like kind of advanced, but something that physicists and chemists use a lot. Analysis, differential geometry, and topology. All of these things are things that have a really rich amount of connections between origami and these subject matters. So what I wanted to end with was a couple of examples. Here, I'll just start playing this, of people actually using origami. This has been a lot of fun for me because for the past 10, 12 years, engineers and physicists have been getting really interested in origami as a way to make applications. So what you're seeing here is some research from the Harvard Microbiotics Lab from 2009, so over 10 years ago now, where they made one crease pattern, and these little discs are kind of like magnets to help hold things together, but the crease lines are wires, and if they electrify them, then they can make this crease pattern fold into different things. So this is one crease pattern that they're able to fold into a boat here, or the thing that you saw first, I forget what it was, but yeah, what was the, it was a boat, and was the other one a hat? Yeah, anyway, it's not a, oh, that this is like an airplane or something like that. What people want to do with this is that they're envisioning origami transformers. Like, could we create some kind of origami structure, much more complicated than this, that could fold into two different things, like a boat or a plane, or yeah. So, and people have done much more with this. So that was 2009. This video is from 2014. Again, the same group at Harvard. I should try to maybe speed this up if I can. It's not giving me any control, so maybe I can't. But this is people trying the same group trying to make an origami walker. So this is something that is literally folding on its own, but it has these engines. But the engines don't come into play until later. What's happening here is that they programmed this thing, they created this thing, and now they're heating it up, and it's creating these folds. You can see it, and this is actually happening kind of slow. This is like 8 times the normal speed of time. And so they're heating this up, and that's making the creases all actuate at different rates at different times. And then eventually, once everything gets folded, the motors kick in, and then this thing can walk away. But it started, yeah, there it goes. It started flat. So so that's kind of cute. So people are actually trying to use origami concepts to make robots, and you might wonder why, but there's a bunch of reasons. So here's another animation I can show you. This is something called the mirror map fold. This is one of the earliest examples of people trying to apply origami. This guy named Korio Miura came up with this fold. I actually have one here to prove to you that this really does work. It takes a large piece of paper and it compacts it to something pretty compact, but it folds and unfolds very nicely. Like this animation is modeling it, you know. Miura, who invented this, wanted to use this as a way to put solar panels in outer space, because you want solar panels to be really big, right? And so, but you can't just send something big into outer space. You have to put it on top of a rocket or inside a capsule or something. And so if you have a way to fold up a large solar panel, put it into a capsule, send it into outer space, and then have a nice way to unfold it without the aid of human hands, then you could conceivably get a really big solar panel thing out there. So that's one way that origami is useful for deployment, you know, of things, maybe in outer space. But for robotics, it's interesting because, again, if you can create a robot from a 2-dimensional sheet that then can fold into a robot that you can use to do something, well, that's easy to manufacture. It's got a certain level of simplicity of construction. And there's some other things going on there too, but the last example I want to show you illustrates. So this is an application I had something to do with. I worked with these people at the University of Massachusetts, Kristen Santangelo and Ryan Hayward, and they came up with this way of folding these things called polymer gels. I'm going to try to go through this quickly, but the real, without getting into details, what they would do is sandwich two layers of stiff polystyrene around a layer of grow animal material. Grow animals swell when you get them wet. Okay, so the middle layer here, that will swell when it gets wet, whereas the blue layers won't. They remain stiff. And they can make these things really, really thin. This is like 1 nanometer thin. These things are really, really tiny. But what they do is they carve these trenches to control where the swelling happens. So wherever there's a trench here on this cross section, if the trench is on the top and it swells, it'll give you a mountain crease. If it's on the bottom and it swells, it'll give you a valley crease. And so they take the mountains and the valleys and they carve them into the top layer and into the mountains are on the top layer, the valleys are on the bottom layer. And then they can actually, by dunking these tiny things into water, make them fold. And the width of the trench that they make, that controls what folding angle you get, how much you want it to fold. So they had a lot of control over this. This was really promising. And when they developed this, they approached some origami people like me and a guy named Robert Lang to say, okay, tell us what we should use for proof of concept. So one thing they did was they made this, that they wanted to make an origami crane, but the problem is they need all the creases to happen at the same time. There is a challenge with this method of how do you make things fold sequentially? But they did this. They got this flapping bird. This is the normal piece of paper, but this is an electron microscope version of their tiny 100 nanometer model. To give you an idea of how small that is, you can see that here. This is this little red dot there, and that thing right next to it, that's a grain of rice. That's how small this is. Okay. In fact, to show you that there's a blow up, that is the crane there. So these things really work. Another thing they wanted to do is have this fold a Miura map fold or Miura Ori, because that's what everyone does in physics. If they get something cool, they want to make a Miura Ori out of it, just because it's kind of a classic model, but also it's a good challenge too. So here you can see the Miura Ori folding and unfolding. This is like less than 1 millimeter wide. This thing is super tiny. And so again, we have to, video recording this is kind of tricky, but that's the nice thing about this is that, yeah, you get it wet, it'll fold up. And then if you dry it out, it'll unfold. So this is repeatable. one thing they asked me to do is come up with something really complicated. They wanted to really say, like, can we do something really complicated? So I gave them this thing, which is like an origami tessellation that makes this 3D thing. This was kind of interesting because I gave them this crease pattern and I gave them information about it, but it didn't work so well at first. And that's because the postdoc they had working on this didn't get the geometry quite right in terms of predicting what folding angles it needed. So I had to do some more work with them. So here that's like not quite folding like it should. But then by making the folding angles more accurate, by getting the geometry to work out a little bit more, they were able to do better. But this was after 15 minutes of swelling, and part of it folded well, other parts didn't. What they found kind of amazing is that just by waiting longer, so after 2 hours, most of it did actually fold up. There was still a little, something going on here, but with more time, they were actually able to get it to work. They did make a video of this unswelling, so they dried it out, and I guess I probably have to hit this, yeah. They let it dry out, and then it boom, unfolded, and then they got it wet again, and it actually worked a lot better the second time. I guess it learned what it was supposed to do. So again, this is an electron microscopy image of this thing, which is again less than 1 millimeter wide. This is interesting because these are soft polymer gels. They're water-based. You could inject these in a human body and it wouldn't care. There's nothing really nasty chemical about these kind of things. So one of the things they're envisioning of using this for is something called targeted drug delivery. Imagine you had, we're trying to fight a cancer tumor site, and you don't, rather than flooding your whole body with chemotherapy or radiation or something like that to try to fight it, imagine instead you could have a little origami ball that closes up around a really toxic cancer-fighting drug, inject that into the human body, and somehow program the creases so that if they reach, say, the pH level of a cancer tumor site, then it will unfold and release the drug in hopes of hitting the tumor site. That's one thing that biological engineers are trying to perfect for medicine. And origami could be a way to actually do that. Anyway, I hope that was interesting, and I'd love to answer questions. If you want to know more, please feel free to email me. There's my email address. And I guess I always have to mention that a lot of the research that I've done here, especially the stuff I've shown you, has been funded by the National Science Foundation. And one of the things they make you do is whenever you talk about it, you have to say, oh, the National Science Foundation. But yeah, there you go. Yay. Any questions or whatever?
Yes, I have a question.
Cool.
So how do you fabricate a lot of these different memory materials, like things that can actually memorize their shapes or memorize configurations? Because I know they're a lot more than just polymer based.
Yeah.
So how are they fabricated in a lab, and can you actually reproduce those fabrications? Because I'm really interested in that stuff.
That's a huge question. There are a number of, and this is where the engineers come in. I mean, these physicists that I worked with, some of them had, or one of them had engineering training as well. That's how they were able to come up with this idea. But there are a lot of engineers that are really interested in finding ideas, ways to fabricate things that will fold predictably, like you say. There's something called shape memory alloys that have been very popular.
Like nitinol?
Yeah, I don't know the chemical composition of a lot of them, but the idea is, yeah, that they take a piece of metal and like the simplest examples are just like tubes of metal or like a paper clip or something like that. But they treat certain parts of it so that when it heats up, it'll fold into a certain shape. And that would be one that's heat activated as opposed to, say, water or some other type of stimulus activated. But they can also do it with a flat sheet using, I think, the same techniques. The problem there is that is getting these things to work predictably when you have lots of creases coming together. The nice thing about this polymer gel technique is that it didn't seem to mind the complexity level at all. With enough time, it would swell into the right kind of thing. But with shape memory alloys, sometimes they fold into kind of the wrong thing. Like some of the vertices might pop in the wrong way and stuff. And so how do you control for that? And that requires another level of technological innovation. But yeah, shape memory alloys is one. I'm trying to think if there are others. There was another one where people were just trying to find ink that they could put on a piece of paper so that again, if in humidity, as it got wet, the ink would contract, and then so you could literally paint your crease pattern on, and that would be another way to do it. But that's folding out of paper as opposed to metal or something more stiff or something like that. But there's tons of ways that people are trying to invent, ways to have things self-fold. The robot I showed you from the Harvard, or those 2 videos from the Harvard lab, those were 2 different techniques they had. One was using electricity along wires to cause a contraction to happen. The other one was heat activated joints that they had between these panels of, I think, like really thin board or something like that. Or maybe it was plastic, I'm not sure. Yeah, but so big question. Yeah. Oh, I see. I think I missed some other questions too. Someone's asked, what was my favorite application of origami in scientific research? I don't really know yet. Well, actually, one thing that I thought was really cool, but it has not been fully made yet, is someone came up with an origami heart stent. So a little origami tube that can fold into an even tinier tube that you could thread into someone's arteries and have it then open up and unclog an artery. It's a great idea. I think there's some people that still want to try to make that work, but it has not yet gone to like no humans have them in their bodies yet. But that'd be kind of cool if you could do that. Yeah. As far as the fascinating things, I think the space applications are the most fascinating things I've seen, because NASA's really interested in this. They actually have, I've met researchers at NASA who do have expertise in origami, and they want there to be solar sails in outer space that unfold, and there's a lot of work being done on that. Nothing has actually been launched that's super origami. Well, so the mirror manifold does exist in some satellites, but NASA is still working on a lot of things and that stuff is really kind of cool. Anything else, or should we should probably move on, I think.
Okay, so if there are no other questions, I think we're just going to move on. Thank you so much for your time.
Yeah, sure.
And our next speaker is Dr. James Tanton. He earned his PhD in mathematics from Princeton University. He is an author, consultant, and ambassador for the MAA, chair of Advisory Council for the National Museum of Mathematics, and the founder of the Global Math Project, an initiative to transform the world's perception of what mathematics should be, which has reached over 6 million students and teachers. Today, he will be talking about some unsolved questions on place value. So without further ado, please welcome Dr. James Tanton.
Well, hello, everyone. Here I am. There we go. Hello, everyone. How's it been today? Sounds like it's been a fascinating day, and I'm so sorry to join in so late, but I'm glad to be here. So thanks very much for inviting me. So let's make this a math experience. I have, how much time do I have? I have 17 minutes. Okay, we'll do something spectacular. Mathematics.
Dr. Tanton, you can take the whole 30 minutes.
No worries. We'll take as long as it takes. We'll see how it goes. All right, so I'm going to share my screen and hope this is going to work just fine. Is everyone seeing a single pen on a piece of paper right now? Can someone give me a thumbs up? Excellent. And I can move my pen around and you're seeing it in live action. All right. So yes, I'm going to talk about place value, a very simple idea, but a very profound one. In fact, I think this is one of humankind's greatest inventions, how to write numbers in place value. So let me give you the story of place value, assuming we know nothing. I'm going to assume zero mathematics. We're going to go back to kindergarten days. So here's a story that's not true. I'm going to begin with a story in a very strange way. When I was a child, I invented a machine, not true. And all my machine was a row of boxes that would go as far to the left as ever I desired. Very strange machine. And being a somewhat strange child, I gave this machine a very strange name. I called it a 2-1 machine, written in a funny backwards way. But I was a young lad, so I knew no different. Backwards is fine. Now, the idea of this machine is you put in dots. It's not going to be very exciting, but you put in one dot. A dot will always go into the rightmost box. So here it comes. Here comes a dot in the rightmost box. Zoom. Not very exciting. It just stays as one dot. However, put in a second dot in the rightmost box. Here it comes. Zoom. Now there are 2 dots in the box. And whenever there are 2 dots in a box, something particularly exciting happens. They explode, kaboom, and disappear. My video stalled. Come on, there we go. They disappear. and are replaced by 1 dot, 1 place over. 2 dots become 1, hence the name 2-1 machine. So hopefully you got it now. This is the name 2-1 machine. And I'm going to say the code for the number 2 is now no dots, no dots, no dots, no dots, 1 dot, 0 dots. I'm going to just say 1, 0 is the code for 2 in a 2-1 machine. Here comes the third dot. I'm going to put in a third dot in the machine. Zoom. Always the rightmost box. So I won't bother writing the leading zeros, but now I'm going to say the code for 3 is 1 dot, 1 dot, 1, 1. Putting in a fourth dot, have a feeling it's going to be particularly exciting. Here it comes. Zoom. 2 dots explode. Kaboom. Replace with 1 dot, 1 place to the left. Kaboom! Replace with 1 dot, 1 place to the left. And there's the code for 4, 1, 0, 0. And I bet you can see in your mind's eye, the code for 5 is going to be 1, 0, 1. Here it comes. Zoom. I bet you can see the code is going to be for 6 is going to be, oh, what's the code for 6 going to be? Can you see it in your mind's eye? Here it comes. Zoom. Kaboom! Dot. 1, 1, 0. And what's the code for 13? We'll just skip some numbers. In fact, type into chat what you think the code for 13 is, because I bet some of you know what's going on. This is a very clever crowd. Actually, I can't read the chat, so I can't even see the chat myself. What sort of numbers are people saying?
Someone said 1101.
1101. Okay. Anyone else say something else? No, everyone's saying that. Okay, you are way cleverer than me. But I'm a young child. I was just having hours of fun working out codes of numbers in a 2-1 machine. But then, in this untrue story, I had a flash of insight because I realized instead of doing a 2-1 machine, I could do a 3-1 machine. I go crazy. 3-1 machine. Put in 1 dot. Zoom. Not very exciting. Put in a second dot. Zoom. Still not very exciting. You need 3 dots to explode, but put in the third dot. Zoom. Now 3 dots in the box explode. Kaboom. To replace by 1 dot, 1 place to the left. 3 is 1, 0. 4 is 1, 1. 5 is 1, 2. 6 is 2, 0. Is that what we're going to be? I'm going to do it. 6 dots. I'm slower than you guys. I bet you guys are faster than me. 6 dots. 3 explode, become 1. Kaboom. Dot. Kaboom. Dot. 2, 0 indeed. All right, clever people. What's 13 in this 3-1 machine? Type into chat. And what's someone saying? Can someone tell me?
Someone said 111.
Okay, if someone says 111, I'm going to believe them, but I haven't actually done it myself. I'll put question marks next to it. Hours of fun working out codes in a 3-1 machine. In fact, I realized I could keep going. I could do a 4-1 machine. I could do a 5-1 machine. I could do a 6-1 machine. But let's go wild. Let's do a 10-1 machine. I'm going to put in 273 dots in a 10-1 machine. And since I've been given the full half hour, I'm actually going to do it. Here comes 273 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. If I really had the patience, I could draw on 273 dots. All right, okay. Now, I bet you're on to me, but I'm still a young child in this story. There's 273 dots. My first question is a yes/no question. Will there be explosions? Yes, there will. How many explosions will there initially be if there's 273 dots in that 10-1 machine? And I bet you're all thinking, 10 will explode, 10 will explode, 10 will explode, 10 will explode. In fact, there'll be 27 explosions. Is that right? Oh, someone nodded. So 27 explosions. Each explosion makes a dot. So kaboom, kapow, gazing, gazoop, gadip. So they're going to make 27 dots over here. So I'm getting bored with dots. Can I just write 27? And will there be any dots left behind? Yes, there'll be 3 dots left behind. I'm essentially saying this. So 27 explosions, there'll be 3 dots behind. Now, will there be some more explosions? Yes, 2 explosions. Kaboom, kapow. Each explosion makes a dot. And this time it leaves, what, 7 behind? 4, 5, 6, 7. 7 dots behind. So the secret code for the number 273 in a 10-1 machine is 273. All right, so what are these machines really doing? Now, maybe to everyone in the audience is clear, what are the machines up to? So just write a phrase or word in the chat box and tell me what these machines really are.
Someone said base and counting.
Base and we're counting, place value counting. Yes, all right. So really to make this clear, I'm going to be really explicit. So we said here in a 2-1 machine that dots here are always worth 1 because I went 1 dot, 1 dot, 1 dot. And then we said 2 dots here are worth 1 here. This dot must be worth 2 of those. It must be worth 2 ones. 2 ones is 2. It must be worth 2. And we said 2 of these, 2 2s, kaboom, makes 1 of those. That must be worth 2 2s. It must be worth 4. And 2 of these, 2 4s, kaboom, make 1 of those. That must be worth 8, 16, 32, and so on. So welcome to base 2. Now, someone in chat was very clever and said 13 was 1 dot, 1 dot, 0 dots, 1 dot. Can you see, and now I mean literally see that that is correct. Can you see that 13 is 1 dot, 1 dot, 0 dot, 1 dot? Yes. 1 8, 1 4, no 2s, 1 1 does indeed make 13. That is correct. Welcome to base 2. Welcome to writing numbers in just zeros and ones. Welcome to what we do with computer science, because computers are based on electrical switches that are either on or off. They only have 2 symbols to work with. Computers use base 2 because it's a lovely way to write all your numbers now in just 2 symbols, like electrical switches on or off. And the 3-1 machine. 3-1 machine, cool. Same idea. Dots here are always worth 1. And now 3 of these makes 1 of those. 3 1s is 3. And 3 of these makes 1 of those. 3 3s is 9. And 3 of these makes 1 of them. It's 27, and so on and so on. 81, 243, 729, etc. Tell me, is 1 1 1 actually correct for 13 in the 3-1 machine? 1 dot, 1 dot, 1 dot. 1 9 and 1 3 and 1 1 does indeed make 13. Beautiful. Welcome to base 3. Welcome to ternary. And people are talking about building optic computers that aren't based on electrical switches, but are actually based on polarized light. They'll be based on light that actually comes in one plane, or it comes in at a 90-degree plane, or there's no light. So if we ever build optic computers, they'll have 3 different states to work with, which is they could write codes with 3 digits, 0, 1s, and 2s. So if we ever went to optic computers, then ternary would be the way we would think about. And then, of course, there's this one, 10-1 machine. You're on me. 1 dot, the dots here are worth 1. 10 of these makes 1 of those. It must be worth 10. 10 10s makes 1 of those. It must be worth 100. 10 hundreds makes 1 of those, 1,000, and so on, and so on, and so on. And in fact, this is the place value that we in the Western world seem to like very much, because we literally say 273. 200s, there they are, 200s. 17. Now, T is short in English for 10. We are literally saying 7 10s, there they are, and 3. So we literally speak 10-1 machine. We literally say 270, 7 10s, and 3. All right, so why do you think our Western culture is so obsessed with the number 10 on matters of counting and arithmetic? What makes us just, we humans, so obsessed with the number 10? Yes, I see people doing it. It's this. We have these things, which we learned to count on very early on. We have 10 of them, in fact. In fact, we even call these things digits. These fingers are called digits. And what do we call these individual symbols? Digits. No coincidence. There are some cultures that went base 20. They actually worked with base 20 instead. Why did some cultures go base 20, do you think? So I don't see the chat, but somebody needs to speak out. What
they said 10 fingers and 10 toes.
Some cultures are very aware they had toes as well. So some cultures went base 20. Some cultures went base 12. Because a lot of cultures realize there's a very good way to count to 12 on one hand. Oh, I've got markers on my fingers already. Okay. Have you ever noticed you've got 4 long fingers, each naturally broken into 3 segments? We've got this great pointer here. A lot of cultures in Southeast Asia and parts of India still count to this day this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Have you ever seen people do that? People do it. In fact, you do it this way. I just did one group of 12. Now I'll do another group of 12. Up, second group of 12. Third group of 12. You can actually count 144 on 2 hands, and people do. So a lot of cultures actually went base 12, which is kind of interesting. In fact, we have a lot of vestiges of base 12 to this day. Have you ever seen this word in English? Dozen. 12 is a very handy number in everyday life, because you're doing matters like trade and weights and measures. 12 is a good number because a lot of the fractions often come up in life. It's like, I want half of something, or a third of something, or a quarter of something. 12 is a good number for everyday fractions. Half of 12 is 6. third of 12 is 4. A quarter of 12 is 3. Good solid numbers. So when you're doing basic fractions of everyday life, 12 is a good number. We even say there's 12 inches in a foot. We say there's 12 hours in a day. Literally 12 hours in a day. They never used to measure time during the night. Sundials didn't work at night. So they said 12 hours in a day, and then they went 12 hours at night as well. So a lot of cultures went base 12. In fact, you can probably tell from my accents, I'm not actually American, I'm Australian. But I happen to know Americans have a bit of base 20 in their lives as well. The Gettysburg Address, Abraham Lincoln, Abe Lincoln. Does anyone know how the Gettysburg Address began?
4
years ago. So the question is, how long ago is 7 years? How many years is that actually? And it turns out score is an old word for 20. Abe Lincoln was actually saying 4 20s and 7 years ago. He was speaking base 20 then. That's 87 years ago. And in fact, if you speak French, how do you say 87 au français? It's actually 87, literally word for word, 4 20s and 7. French people still speak base 20 to this day to some degree. Anyhow, I'm giving you a speed experience of all of school mathematics and all the maths that we know today before I get to some research questions. Let me just show you, I love base 10. In fact, you can do really fabulously quirky stuff. 253 plus 122. Let's go to grade 2 or grade 3. I don't know what grade we're in. But clearly that's what, 3, 7, 5? Am I right? Okay. Did you notice anything strange about what I just did then? We were taught in school to go right to left, which I thought as a kid was very strange because in every class I was being taught to read left to right, except math class. And they said, no, you go right to left in math. I thought, that's strange. Why is that? Well, obviously it's for things like this. So I did 253, and we've made it nasty, like 100, I don't know, 68. Well, okay, 2 plus 1 is 3, 5 plus 6 is 11, 8 plus 3 is 11. The answer is 311. And I'm correct, and I'm even saying it correctly. But if I draw a dots and boxes picture of this, 253, 5 tens, and 3. If I say add 1 more 100, no worries, 1 more 100. Add 6 more tens, no worries, here's 6 more tens. Add 8 more ones, piece of cake, I'll add 8 more ones. I will indeed have 3 hundreds, 3. I'll have 11 tens, 11, and I'll have 11 ones. 311 is absolutely solid and correct. I have a PhD in mathematics. I give that my stamp of approval. That's my fist of a stamp of approval. The trouble is, society thinks that's weird. So what could I do to fix that answer up for society's sake? So someone must be typing something into the chat.
One said 421.
Okay, so you must have done some work there.
Form it into ones.
Okay, so let's explode some 10 dots, because you're right, 10 dots explode, kaboom, leaving what, 1 dot behind, an extra dot there. So the answer is 411. That is still solid and correct. There's nothing wrong with that answer. Okay, but I'm going to explode again because society thinks it's weird. 10 dots explode, kaboom. I'll make that 421. 421. English is weird, by the way. They don't like the word tutti. We like to say 20 instead, because English is a very hard language. I have no idea how people learn English as a second language. Okay, so my point is we can do fabulous stuff in mathematics in base 10. All right, so I could go through the entire school curriculum, but I'm a mathematician. I like to play. Place value, no worries. We can be quirky and say answers like 311. But let me ask this question for the remaining few minutes of today. We think we understand place value. We think everything Tantan is doing right now is straightforward and easy. So let's get quirky. So I did a 2-1 machine. I did a 3-1 machine. I did a 10-1 machine. Here's my first question. Is a 1-1 machine interesting? And this is a very subjective question. What does interesting mean? I don't know. Is it interesting to you? Put in 1 dot. Kaboom, 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 kaboom. Off to infinity. I don't know if that's interesting to you or not, but it's kind of untamable. So I won't do that. I won't do that. Okay, that seems hard to control. What if I mix the numbers this way? What if I did a 1-2 machine? Is that interesting? 1 dot. Kaboom! 2 dots. Kaboom! 4 dots. Kaboom, 8 dots. Again, it's just going off to infinity, but this time it's like, so it keeps expanding, like exploding, like all the shrapnel go to infinity. So it seems untamable. That seems hard. All right, okay. So 1, 1 machine, 2, 1 machine. Okay, that seems untamable. What if I did a mixture then of what I was doing before, like a mixture of like 3 and 2? What if I did a 3, 2 machine? Ooh, is that interesting? And now it makes me pause. Okay, I'm going to be back to the beginning. So let's go to the beginning. Put in 1 dot, 1 dot, not very exciting. Put in a second dot, zoom. Not very exciting because you need 3 dots to explode to become 2. So put in a third dot, zoom. Kaboom! 3 dots explode to become 2. So I guess the code for 3 is 2, 0. 4. Zoom. 2, 1. 5. Zoom. 2, 2. 6. I have a feeling putting in a 6 dot is going to be particularly exciting. In the chat, typed in what the code for 6 is going to be in a 2, 1 machine, in a 3, 2 machine, you think?
The consensus is 100. Oh, no. Okay. Some people said 100. Some people said 110.
Let's do it. Okay, here's 5 is 2, 2. Here comes the 6 dot. Zoom. Kaboom! 3 explode, become 2. Oh, 3 explode, leaving 1 behind to become 2. Whoa. 13 is 2, 1. So 6 is 2, 1, 0. Because my brain wants to go to 13. You were so quick with 13 2 times before. Okay, everyone, what's the code for 13 in this machine all of a sudden? Are we speedy? No, I'm looking at the faces. We're getting like, also, who knows? All right, so I will do it. I will be kindest. I'm going to physically do it for us on the screen. Let's put in 13 dots. I'm going to literally put them in. I've got enough time to actually do it. There's 13 dots. 3 explode, kaboom, become 2. 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 And we've got 1 dot left behind. 3 explode, kaboom, become 2. 3 explode, kaboom, become 2. And 2 left behind. 3 explode, kaboom, bit messy, become 2. 13 is 2 dots, 1 dot, 2 dots, 1 dot. Okay, so the real question obviously is, what is this machine? I can work out code to all these numbers, but what's this machine doing? Is this place value? Is this still a base? Are we still writing numbers in some clever way?
It's like you're converting into base 1.5.
Base 1.5?
Yeah, because when you're switching from, when you're using the machine to go from 3 to 2, each place value is replacing the value of 3 with 2.
So it's obvious. Okay, all right, okay. You are faster than me, so I'm going to be very slow. So I'm going to do what we did before. We said a dot here is worth 1. And a dot here is, I don't know what it's worth. I'm going to write W for I don't know what it is. But we do know that 3 of these, 3 1s, should be the same as kaboom, 2 W's. Ah, you're right, sir. W must be 1.5, 3 halves. Okay, next one. 3 3.5s. 3 3.5s should be the same as, or what to call this one? I'll call it, I know, X. Everyone calls it X. It's the same as 2 of these. Kaboom. So 3 3.5 is the same as 2 X's. So what's X have to be? I guess if I divide both sides by 2, it's 3 halves squared. You're right. It's the next power of 3 halves. Whoa. And if you keep going, this is the next power of 3 halves. 3 halves cubed, 27 eighths, 9 fourths, 3 halves, 1. This freaks me out because apparently this is what, 27 eighths. This is 9 fourths. This is 3 halves, and this is 1. Apparently, if I did 2 of these guys, 2 27 eighths, 1 of these guys, 1 9 fourths, 2 3 halves, and 1 1, I get a beautiful whole number 13 in the end, which actually my intuition says is freaky. Why would working with these horrible fractions give me whole numbers on the nose in the end? But by the way, is 2 27 eighths, I should check this, plus 1 9/4 plus 2 3/2 plus 1 1. Is that actually 13? Can we just double check? Is it true? Yeah, it is. I see 27/4 plus 9/4. That makes 36/4. That's 9. Plus 3 plus 1. That's 13. Absolutely. Welcome to base 1.5. Welcome to base 1.5. I don't know when you'd ever need base 1.5 in your life, but there it is. You could actually do base 1.5 if you want to. In fact, we could have done this. We said that 6 was 210. So we could have done the arithmetic I was doing before. 6 plus 6 plus 1. That should be 13. Well, let's do it. 2 plus 2 is 4. 1 plus 1 is 2. 0 plus 0 plus 1 is 1. I went left to right again. But what would happen to that 4? Kaboom! 3 would explode, leaving 1 behind, an extra 2 over. Bingo. That's 2 1 2 1 again. You can do arithmetic in base 1.5 if you want to. In fact, if you want to, you can take all your latest textbooks in math and convert everything to base 1.5 if you like. Optional homework, do that. But let me tell you one thing. Mathematicians to this day do not understand base 1.5. People do not understand the basic powers of the most simple fraction there is. The simple fraction 1.5, people do not understand it. Example, let me show you something. Here I wrote out all the codes of the first, 36 numbers in base 1.5. There they are. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, so on and so on and so on. So 0 is the first one-digit answer. 3 is the first two-digit answer. 6 is the first three-digit answer. Here's the first four-digit number, 9. 15 is the first five-digit answer. Okay, what's the next number? It's along here, and there's the first six-digit answer, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Do you have any predictions on what the next digit number is going to be? So we've got 3, 6, 9, 15, 21, 24. Do you see any pattern to that sequence of numbers? What if anyone's typing anything? Because there might be a pattern there.
People said multiples of 3.
Definitely multiples of 3.
39.
Yep. Oh, 39. Oh, okay. What makes someone say 39
Yeah,
there?
someone said Fibonacci too.
Fibonacci. It's like, okay, because 3 plus 6 is 9, 6 plus 9 is 15, 9 plus 15 is 24, 15 plus 24 is 39.
39.
So you pick one's 39. That'll be this one. Beautiful. P is wrong. It's 36. Whoa. Turns out this pattern I'm about to go through is very strange. No one actually understands the pattern. The next number is 170. The next number is 278. The next number is, I've got written down somewhere, 422. That's 494. No one understands this pattern. People know how to get from one term to the next. They don't know a general formula for this. Say, if I want to work out the 100th term of the sequence, what's the explicit formula for this? No one knows. And it's all it is about a basic power of 1.5. We don't understand the basic powers of 1.5. My favorite number for a lot of people is 17. So it's a pretty good number. Here's the number 17. It's 21012. It's a palindrome. People only know 10 examples of palindromes in base 1.5. There's an example, there's an example, there's an example, there's an example. And that's 5 of them. Only 10 examples are known. No one knows, as far as I'm aware, if there's any other palindromes beyond the 10 that we know of in base 1.5. In fact, it keeps going strong. So I'm going to stop here, but if this is intriguing to you, there's a whole worldwide phenomenon going on called exploding dots. If you just Google exploding dots, you can find some stuff and definitely get to the 3-2 machine and see a whole host of unsolved questions that people don't know about place value. Because all I did today was you probably thought to me, like, what is this guy doing? He's just doing binary. What's this guy doing? He's just doing ternary, wherever my ternary sheet went. I lost my ternary sheet. Base 3, I did base 3 somewhere. But then if I just mix them up and just be a playful mathematician, as I am, then we're in the world of unsolved territory. So even what elementary school mathematics is all about, just place value, how we write numbers, we think we understand everything, it's an invitation for so much more. So mathematics is what my dearest discipline. I love the fact that I know nothing. Every question I feel like I solve in maths is actually telling me there's so much more I don't know. It's the most humbling pursuit there is. You just feel like you're in this abyss of nothingness endlessly. And it's kind of great. All right, so thanks so much for having me come today. That's my message for what the M means in STEM. It's the abyss. Welcome to the abyss at the M, the fourth letter in STEM. Thank you so much, everyone. This has been a real delight, and thanks for having me today.
Thank you so much for
Thank you
coming
so
today.
much.
Yeah. Does anyone have any questions?
Thank you.
You're so welcome. Thank you. Yes, that was a whirlwind review of exploding dots. Yes, exploding dots has become a bit of a thing worldwide. So you'll easily find it if you want to look for it. Great.
Oh, someone asked if machines can be used to help visualize logarithms.
So think about what's a logarithm base 10. The logarithm base 10 is basically a little bit of bump, the number of digits you see. So up by 1. So the logarithm of 100 is 2, but it's actually a 3-digit number. In fact, all the numbers to 3 digits have a basic logarithm, integer part being 2. So in some sense, yes, you can literally see the logarithm, at least the integer part of a logarithm, by just counting how many boxes you use to write the number. So what would be very interesting though, was the base 1.5 type logarithm of things. I don't personally know what structure they might have, because I think it's kind of curious. So yes, the number of digits is the very question I was asking. How do you know the number of digits in base 1.5? Which is really telling you about something about the logarithm base 1.5. Welcome to unsolved territory. Great. Seems like everyone's just had a mindful just then. So thanks so much for having me. And if you want to find me on email, I'm very easy to find. I'm happy to chat on email. I'm slow to respond because I get a lot of emails, but I do respond. So feel free to reach out to me. All right. Thanks, everyone. This has been a real joy.
Yeah. Once again,
Thank you so much, Dr. Chanton.
You're so welcome.
I just want to say, oh yeah. Oh, I just wanted to say I'm like a bio person, and honestly, after that math, like all of our math speakers, I'm starting to like want to convert. So.
You'll do both. That's the answer. Do it all.
Oh yeah, I know, of course.
Life is full of learning and joy. Go for it. Thank you. That's a compliment. I really appreciate it. All right. Have a good rest of the evening and a good rest of the weekend. There's a lot going on. I'm so impressed with the schedule. This is very impressive.
Thank you so much.
You're welcome. Bye, all.
Bye. Thank you.
And I think now we will be transitioning to the math competition. So yeah, we're going to split into 2 breakout rooms, and then it'll be a Kahoot. Diana, are you, please?
Did everyone get the invite?
Wait, you made sure that we're in different rooms.
Yeah, I am right now. Hold on. Catherine, Lou, Ari, and Mather. Yeah.
Okay.
To whoever is watching this later on YouTube, right now we're just playing the math competition. So in like 30-ish minutes, William Lin will be joining us.
Is it too late to join the math competition? Like, did they already start?
You can, yeah, they already started. You can join, but you'll just be like a few questions behind, I think, too.
Okay. How would I join?
I just sent you an invitation. What is the game thing? Wait, Harriet and Ryan, are you guys trying to join too? Okay. Go to the calendar invite. Are either of you trying to join? Oh, okay. Whoever's watching this video in the future, just skip like 30 minutes ahead.
Yeah, so you guys can just chill for a bit while we wait for the other room to come back, and then we have one more speaker still. What did you guys think of the math speakers we just had?
Ew.
Michael, what do you think of the math speakers we just had?
Oh, the math speakers were awesome. Totally sick. Never seen them before, but they were awesome.
Yeah, Raga, what do you think?
I have the same thing as Michael. Like, I've never seen these things of you guys before, but like, they were so good.
After this, I've reconsidered my path on math. I'm actually going to literacy now.
Oh
Bye,
my
guys.
god, yeah.
I'm leaving this world.
Are you guys all in the Slack workspace? Because that's where we're going to be announcing the winners.
Do you offer help with like the types of questions that you put in the Kahoot, or
Oh yeah, do you want to give us
Sorry, what?
solutions
what if you
afterward?
like the
Oh, like an answer key?
I didn't write up solutions, but I can get that to you soon, maybe.
Okay.
Yeah. Wait, the question's like too hard?
Like two of
Should
them, right?
I mean,
Yeah, two of them, right? Yeah.
yeah.
I like to think I'm good at math.
That
Yeah,
last one, oh my god.
yeah, I can. Should I make it easier next time? I don't know. Wait, there's like AMC 10, 12. Yeah. Right?
Yeah.
Wait, is William here?
No, we're waiting for him. So I
Okay.
mean, he's gonna come. He's gonna be here soon.
Hey, friends from the math comp, you guys should stay. If you don't know William Lin, he's the IOI finalist from last year. Super cool. He participated in AMC too, right?
Yeah, and Yusuko.
Yeah, AMC Yusuko star. So don't.
Oh
let him
yeah,
fool you.
and you should check his YouTube channel.
IOI. It's like
It's
like
international.
IMO.
Oh yeah. Okay.
It's like IMO but for computer science.
Yeah, it's International Olympiad in Informatics. So it's like
Yeah.
international coding competition.
Innovative online industries.
Yes, IOI is actually a huge corporation, a mega
Yeah,
corporation.
I think I've seen that before. Well, we'll have to just wait until, because he's all the way in Taiwan right now. Oh, and now he's seen it, so now he's going to probably join soon.
The scores actually need to be calculated.
He's here now. He's here. Okay.
Okay.
So
Wait, sorry. Really briefly, just before, I know we're live streaming, but Matthew, Ariane, are you able to see Matthew's scores?
Yeah, I am.
Like
Both
from
of them.
before he was kicked? So
yeah.
you can add them up. Okay, so
yeah.
Matthew, you're good. We can add them up. Okay, sorry, William. We just finished the math competition.
Oh, it's fine. It's totally fine.
So, okay, let's start. Hello, everyone. I can just skip the main part. Okay. So, okay. With that being said, I'm excited to introduce our speaker, William Lin, who is an incoming freshman at MIT studying computer science. He has participated in various computing-related contests like AMC, which is mostly math, USICO, and the International Olympiad in Informatics, and he was a 2019 silver medalist. He also is an incredible YouTuber. You should check out his videos. We are excited to have him as a speaker, and now, William, please take it away.
Okay, thank you very much for the introduction. Let me see how. Okay. Give me a second. Wait a sec. Okay. Okay, so, 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 okay, so Okay, can everyone see the slide?
Yeah.
Okay, cool. So hello everyone. Today I'm very happy to be here to talk about and share my experiences with computer science Olympiads in high school. I'm William from Taiwan. I'm an incoming freshman at MIT and I'm planning to study in computer science. I'm very enthusiastic about programming and I've been doing it since I was in 3rd grade. And I've participated in several contests in high school. Most notably, I was a silver medalist in IOI last year, and that is what I'll mostly be talking about today.
Oh yeah, William, we
Oh.
can see your speaker notes if you don't want to.
Okay, that's.
It's okay if you want.
I didn't expect that, but.
Oh, I mean, yeah, it's fine either way.
Wait, is it like, does it block the entire screen or?
It's good now.
No, it's good. It's good.
Wait, because on my screen it shows the speaker note. The speaker notes is the entire screen. So.
Oh, for us now, like we don't see it at all.
Yeah, we
Before
only see
it was
the.
like a small box thing.
Let me. I didn't. Did I share it wrong? Does this work now or?
We can still see.
What if you share the slides with us and then you can have your notes?
Oh, okay, sure.
Oh yeah, we can present it.
Okay, that would be.
Okay, William. Just send it into the Zoom chat and I'll put it on my screen.
Yeah, you can send it to just Arun. Yeah, I remember.
Okay, great. Just tell me when to, switch slide. Switch.
Okay, so yeah, we can move on to the next slide now.
Okay. Great. Okay.
So Olympiads are similar to Olympics, but instead of being about sports, Olympiads are academic contests. There are many competitions and programs that have the word Olympiad in their names, but I'm mostly referring to the International Science Olympiad for the rest of this presentation. The 5 most well-known or important of these Olympiads are IMO for math, IOI for CS, IPHO for physics, ICHO for chemistry, and IBO for biology. To qualify for one of these Olympiads, first you need to be a high school student, then you would need to participate in your national Olympiad. The Olympiad organization in your country will then select 4 to 6 students to, depending on the Olympiad, to represent your country in the International Olympiad. The International Olympiad consists of 2 contest days with about a 5-hour contest on each day. Based on the ranking, contestants are given gold, silver, and bronze medals. And unlike some other contests, it's not like the first place is given gold, the second place is given silver, and the third place is given bronze. Instead, the prizes are pretty generous. So approximately the top 1/12 are given gold, the next 1/6 are given silver, and the next 1/4 are given bronze. Okay. And even though these Olympiads are only for secondary school students, they have the purpose of challenging the best students around the world. So these contests have extremely high standards. As a result, this is often used to help with college admissions. For example, in the US, a disproportionately large amount of medalists get into top universities. And also in Taiwan, obtaining a medal will guarantee admission into National Taiwan University, which is the best university here. Obviously, college admissions shouldn't be why you're doing this. but it definitely does justify spending more time on these over other things like schoolwork, especially to parents who care a lot about college admissions. One thing to note is that even though these contests are big and prestigious, they are limited in what they test. A 5-hour contest may seem like a very long time when compared to tests in school, but if you compare it to projects in real life, 5 hours is pretty short and you can't really do anything from it. So, and also unlike some other types of contests, Olympiads are very objective in their grading. So you'll be solving a given set of problems instead of making projects or doing research, as those are hard to compare objectively to each other. Okay, next. The International Olympiad in Informatics, or IOI for short, is considered the CS Olympiad. I don't exactly know why it's called informatics, but it might have something to do with how the contest doesn't cover all topics in computer science due to the constraint of Olympiads that I mentioned earlier. IOI is mostly about algorithms and data structures in theoretical computer science, and it is basically a competitive programming contest for secondary school students. And I'll explain more about competitive programming later. It doesn't include a lot of the other important and interesting topics in CS, such as machine learning, computer systems, and cryptography. Next. Since I expected a significant portion of the audience to be from the US, and also because I qualified for IOI through the US, I'll be briefly introducing the USA Computing Olympiad, which is the national Olympiad for the US. There are 4 divisions in USACO, which are bronze, silver, gold, and platinum, with the platinum division being the hardest. There are 4 contests in a year, and after those 4 contests, the top 20-something students are invited as finalists for the camp. And in the camp, one group of the students will be taking lessons, while the other group will be taking more contests for selecting the 4 students to represent the US at the IOI. Next slide. Okay, so I mentioned competitive programming earlier, so I'll explain more about it here. In a contest, you are given multiple problems, and for each problem, you need to write a program to solve that problem. Your program is tested automatically by running it with certain input data and making sure that the output data your program returns is correct. In addition to the correctness of your program, time usage and memory usage are also taken into account. So you need to make sure that your program doesn't take too long to run or use too much memory. For some people, including myself, these contests are actually pretty fun and exciting. So I consider these contests to be just like any other sport or video game. On an unrelated note, if you actually want to see what happens in a contest, then you can search my name on YouTube and you can find some of my contest recordings and some other videos. Next slide. So in competitive programming, there are 3 groups of skills that you will learn and need as you do it, namely programming, algorithms, data structures, math, and problem solving. Next slide. So obviously, as the name suggests, you're going to be programming when you do competitive programming. This skill is one that you should definitely develop before starting competitive programming, but naturally, you'll continue to develop it afterwards. The most frustrating thing about competitive programming is that when you submit your program and the judge says that your program doesn't give the correct output, they won't tell you what input they gave to your program to cause it to fail. So you kind of have to guess and try to find flaws in your program, which is very hard if you don't have enough debugging experience. And after you find the flaw, you still need to identify the cause and fix it. And so this is one aspect which is really important in competitive programming. And the last thing you know is that unfortunately, not all languages were made equal. And for reasons mostly because of speed, C++ is the best language and most common for competitive programming, followed by Java and Python. If you already know Java or Python, you don't need to switch languages yet, but I would switch from Python after making USACO Silver or Gold, and I would switch from Java after making USACO Platinum. So the idea is that if you already know a bit of programming in Java or Python, then you typically want to focus on the other two skills first before optimizing this part. Okay, next slide. As I mentioned earlier, your program can't be too slow or use too much memory when the judge runs it. So this is where a good knowledge of algorithms and data structures comes into play. You need to have a good knowledge of algorithms as well as the ability to be able to modify existing algorithms or even come up with your own algorithms to make your program efficient enough. Maybe you haven't heard of algorithms and data structures that much because of all the news which talk about AI and machine learning, but they're actually a very important topic in computer science. And if you end up pursuing a computer science degree in the future, you'll definitely encounter a few classes related to this topic. Next slide. Last thing about competitive programming, which may be a bit surprising for some people, is that it requires math and problem solving. Because of this, if you happen to have experience with the AMC, the AIME, USMO, or even the IMO, then you start competitive programming with a pretty decent advantage. Personally, I qualified for AIME when I started competitive programming. However, this is still a skill that can definitely be improved while doing competitive programming. So I wouldn't worry too much if I hadn't touched the math contest yet. I know that some people might not like math that much, but you're going to have to deal with math anyways while you're learning about algorithms and data structures. It's mostly about discrete math, which includes combinatorics, graph theory, and number theory. And it's more like working with logic puzzles instead of the regular math, which most people see in school. On an unrelated note, I actually find math taught in school somewhat boring, so there's definitely the possibility that you might find some other topics in math interesting. You just need to go out there and try to learn more. Next slide. So to illustrate exactly what I mean by discrete math and logic puzzles, I have a relatively simple example of a math problem here. You start off with an 8x8 chessboard. For some reason, your chessboard is missing two opposite corners as shown below. You have 31 dominoes and you want to tell what's left of the chessboard with these dominoes. And a domino is a 2x1 tile. And is it possible to do it or not? As you can see, this looks much more like a logic puzzle than some math problem that you give in school. And if people are interested in the solution, I can come back to it later. Next slide. There are many other competitive programming contests for high school students. For example, for students in the US, there's the Virginia Tech High School Programming Competition, and in other countries, there will definitely be other local competitions for high schoolers as well. And these contests don't just stop in high school. In college, there's also the ACM ICPC, which I'll be looking forward to. And on top of that, there are also online contests. For example, the website Codeforces, which is a well-known competitive programming website, frequently hosts contests. Google and Facebook both have a series of contests that they run every year. More specifically, there's the Google Code Jam, Google Kickstart, and the Facebook Hacker Cup. Two main reasons why people do college and online contests are that they can look good on your resume and they prepare you for technical interviews from big tech companies. Next slide. Okay, so the situation for competitive programming depends on the country or school that you're in. So for example, in Taiwan, if you're in a local school, which is hard to get into, then they usually have teachers, teachers and clubs, which will help you with every Olympiad. But I don't see so much of this in high schools in the US. In most cases, it's really hard to find support for competitive programming in real life since it's not something which is widely done. You'll have to find everything online. So if you want to learn some new concept, you would just search it on Google. And so, for example, if I want to learn what merge sort is, then I'll just search on Google, how does merge sort work? And there would be a bunch of articles, and I just read them all until I understand it. Yeah, it's basically that simple. And if you're actually interested in starting competitive programming after this presentation ends, you can just search on Google how to start competitive programming. And you'll also find more than enough resources to start with. Next slide. And this also applies to programming in general. If you're just trying to learn to program, there definitely are classes in school that will teach you how to program, but you don't really have to limit yourself to classes in school or college. The current education system, I feel like, is far behind our rapidly changing society. For example, I believe that students don't really learn to program early enough, and there isn't a greater emphasis on programming in school. If you want to become more competitive, then if you want to become more competent, then there's a lot that you can do by yourself outside of school. Then there's also college, which used to be valuable, but now it's not as valuable because information is now much more easily accessible outside of traditional education. There are people out there who graduated with different majors, such as mechanical engineering in college, but then they decided to switch to software engineering due to reasons such as not being able to find a job or not having enough pay. And just go to a coding boot camp for about a year. And after that, they are trained with the necessary skills to become a software engineer. College costs a lot more than these boot camps, but the education you get there isn't as valuable as it was in the past. And right now, I feel like most people go there just for the diploma and the networking. So in conclusion, with the proper dedication and motivation, anyone could learn a lot from using online resources. Next slide. One thing to note about competitive programming for beginners is that its learning curve is very high. Programming is already very hard to learn. It's almost like a new language. And as I said earlier, debugging in competitive programming is very hard. Then you have algorithms and data structures, which is a completely new topic for most people. And on top of that, you also have math and problem solving, which can be hard for a lot of people. So everything about competitive programming is hard to learn. So a lot of effort is required. So it's important to take this into account and to not be discouraged. Next. Another thing that causes a lot of discouragement is the score distributions of these Olympiads. From tests in school, you probably expect a majority of the students to earn around 80 to 90%, which is shown by the graph on the left. The graph on the right, however, shows the score distribution of a past USACO contest. And as you can see, a lot of the people have pretty low scores. School tests consist of relatively boring tasks and focuses much more on memorization, whereas Olympiads contain a lot more problem solving. Definitely takes a lot of time to get better at problem solving, but it's the difficulty of the Olympiads which gives them their value. Next. So some suggestions I have for students which are interested in CS. If you have some spare time, then you can definitely give competitive programming a try. It definitely does not hurt to learn some new skills, and you might even enjoy it after trying it. If you're looking to excel in competitive programming, note that it will take a lot of time to master the various skills that are essential to competitive programming. And as I said earlier, I started programming in 3rd grade, so I already had a lot of experience. And lastly, as for general topics in CS, if you haven't already done so, try to get into whatever you are interested in, whether it be web development, machine learning, AI, or cryptography, by just searching for information about it online. And you'll be surprised about how much information you can learn on Google outside of classes. And next slide. So this is, I finished my slides, and if anyone has any questions, I'd be happy to answer them.
Do you have any tips for college apps? You know, that time of year.
This is an interesting question because
I know it's kind of loaded, but like, okay, specifically like for CS maybe, if that helps.
CS. I feel like you definitely, to be honest, I don't know about the general, I don't know about advice for the general public, because I heard that a lot of people who get admitted for CS actually have never coded in high school or before that. So I would definitely like to see more people start coding earlier, but it just confuses me how I can't really say that tell people to go code for college apps because I don't actually know if it works. So maybe it might be the case that studying more for standardized tests or working more on your college essay, maybe that actually helps more, and I would not know. But if you're interested in a particular subject, if you happen to be interested in a particular subject, then it's probably worth more to go for that subject instead of the other things like standardized testing and essays, because you also get to pursue your passion, and it will end up helping you in your career in the future.
Colin.
I have another question. What's one challenge of running your YouTube channel? Like knowing how big it is, that's why.
One challenge about running my YouTube channel.
Yeah, any challenge, anything you faced. Dilemmas.
I've never thought about this. It's probably just, I would say it's coming up with new and interesting content, because coming up with good and interesting ideas often isn't that's a very hard, that's something which is hard for me. So yeah, I guess that'd be my number one challenge in running a YouTube channel.
So we have two questions. The first one says, what are you going to specialize at MIT?
I actually don't know. there's a lot of things that I could get into, such as which are common for CS majors, such as software engineering, quant firms, and there's also research. So I think during college, I heard that the best strategy is to try to expand and uh, just try to experience some of every possible thing out there. And that's what I'm going to do. So I'll probably try to get an internship and also do um, some research. And based on that, I'll see what I like. And after that, I'll hopefully have a better idea of what I want to pursue in the future.
Another question is, do students in Taiwan learn coding much earlier?
Students in Taiwan do not learn coding much earlier. It just happens that not that I'm aware of. It just happened that I got into it much earlier than others.
And then another one is, why are you choosing to go to college for CS if you're already so good at, or have such a good background in it?
So, as I said earlier, there's also research which I might want to get into. And if I end up wanting to get like a PhD or something, then you kind of have to go through the college route. And I guess there's also like getting a diploma that's and networking, as I said earlier, is somewhat important. And lastly, there's also pressure from my parents. I think they really want me to go to college. So I'm just like, for all the reasons above that I mentioned earlier, I decided that I'll just go through college and see what happens. At least try out like a year or so.
Okay. And then here, there are a few more. How much training does it usually take to be prepared for IMO, since I really want to take it? Says someone.
For the IMO, I'm not really sure because I don't have that much experience with it. But from what I've seen of other IMO contestants, they usually start really early. They start training really early in primary school. So you often see them training for contests in primary school, and then in middle school, they still do contests, like for example, math counts. And then in high school, they continue with the series of AMC contests. And yeah, basically they start at a really young age. I don't know how much practice they put in per day, but the general trend is that they start pretty early.
Okay, and then why did you choose MIT in particular? What did they have that appealed to you?
It was mostly the community. So a lot of my other friends that I made in these competitions, they also ended up going to MIT. So I decided that it would probably be a good place for me to go to.
And then another person says, do you want to start your own company before graduation? Is that graduation from college or? Oh yeah, definitely.
So I don't necessarily see why it has to be before graduation, but if something happens to come up, then maybe I could do it before graduation. About like starting my own company in general, that's another possible that's another possible thing that I could do in the future, and it'll have to depend on my experiences in the next few years to determine exactly what I want to pursue.
Okay, so are there any last questions?
What do you think is like the biggest thing that helped you get like super good at IOI and programming?
Biggest
Like
thing
any
is
resources or
resources. I did most of my practice on code courses, and yeah, I would say that's probably that might be the only problem set or website you need.
Okay, so any questions? Any last questions? Okay. Thank you, William, so much. We know how big
Okay.
you are, and oh, there's
another one.
What was it like?
What was it like?
What was it like filling out the MIT application? Like treacherous, hard?
The MIT application was better than other applications because was it? Like, I really did not like the huge essay on the Common App, and that was, and the essay on Common App was the prompt was somewhat vague, so I had a really hard time with that, and I felt like the essays for MIT were more objective, so the essays for writing the essays for MIT wasn't as difficult, or it wasn't as difficult for me as writing essays for some of my other schools.
Okay, Ivan asks, have you tried those Google and Amazon interview coding websites? I think you had a video on it, I think. Pretty sure I saw one like that.
Interview websites. I've tried, for example, LeetCode, which is pretty big in interview preparation.
The same guy asked, what do you think about Stanford's computer science program?
I don't really know much about Stanford's computer science program, so I can't even really answer much about MIT's computer science program either.
Wait, what was what was your second choice?
Second choice was, it was more like I only wanted to make MIT, and then the other schools were like forced by my parents. The other schools, I applied to other schools because they're either safeties or my parents forced me to apply to them. So I don't necessarily have a second choice. If I didn't get into MIT, like my parents would probably just tell me to choose the one with the next highest ranking. So I guess you could count that as a second choice.
Okay, I think those are all the questions.
You guys should check out William's YouTube channel for real.
Yeah, it's great. Like he posts like almost like stream like videos on his competitions for like the Google competitions. I saw that one, and they're really interesting. Like the way he solves them. Yeah. So thanks a lot.
Hey, thank you.
Thanks so much,
a lot
William.
for having.
Thank you.
Yeah, no problem. I had a great time here. Have a good day, everyone.
Someone says you're cool. Yeah.
Yeah.
Thanks.
Wait, is your name Yvonne? Ivan? Or Ivan? Dude, who's it? Well, no, I know it's Ivan, but like some people say like Yvonne. Ivan, right? Are you okay? Do you go to Stanford or UCB?
So this says UCB.
Oh, okay. Wait, then why do you keep talking about Stanford?
About Stanford a lot, so we're just wondering.
Like, I'm just curious. All right. So wait, are you going to Stanford, or are you just like curious? Oh, okay. You're just curious.
Okay.
Got it.
Nice.
Wait, is UC?
Oh,
Is
yeah.
UC be Berkeley, right?
Yeah,
No,
it's
John.
Berkeley. No, it's
Okay.
Berkeley.
I will be. wait.
You will
You.
Wait, you will be what?
Like,
Wait, what is this?
we were talking about Stanford undergrad.
Thanks, Matthew.
Okay, well,
There's-
we
Yeah,
should
thank you,
probably
Matthew.
end kind of thing.
Yeah,
and
wait,
for some
oh,
people
just
maybe.
like a wrap up.
Yeah.
So you guys, I hope you guys all know like STEM World's happening tomorrow. If you guys are interested, I'm also adding everyone to like a calendar invite because a lot of people forgot about STEM World. So you'll be getting a calendar invite pretty soon. Thank you to everyone who came. I know some people have been here for like many hours.
The
Like
entire
Ivan, I
day,
think
some
you've
people.
been here for a pretty long time. I know Mark was here since 8 a.m. So.
And Raghav, you've been on like the YouTube.
Yeah.
Yeah.
Harriet.
Yeah. So good morning.
Good
Yes.
morning,
So
guys.
thank you guys so much. Thank you so much.
Yeah, we hope you enjoyed it and we hope to see you tomorrow. Thank you.
Yeah.
Okay. Wait. If you guys want to hang out and talk about like your